Okay, let's get started. Hi guys, welcome to Zero to Hero Security class. This is week number 9. Let me share my whiteboard. This guy. Okay, so that's the meeting number 9. And today we're gonna continue talking about VPNs. Specifically, I need to finish the topic about DMVPN. So the remaining part is first off, I need to spend some time talking about MTU issues when you use tunnels. So MTU in DMVPN, because whenever you see the recommended config for DMVPN, you will probably see that there is a MTU IP MTU command under the tunnel interface, lowering the MTU to some value. So we need to discuss here what's the issue and how we can prevent the MTU issues with DMVPN or generally in GRE over IPsec. And then I will move on and talk about DMVPN high availability. So how we can create a more resilient DMVPN topology, basically by increasing number of hubs. There are no single DMVPN deployment with a one hub only. We usually have 2 hubs or even more if you really need that, but or maybe if you have a DMVPN hub hierarchy or something like that. So I will be talking about HA. I also installed an additional router in my topology in the lab to show you how we can do dual hub scenario. Then we move to the new technology that will allow us to encrypt traffic data in a wide area networks, which is a get VPN. Right, we spent a bunch of time talking about that. It's quite important for those of you who are trying to just encrypt your wide area network, which is not through the internet, but built using different technologies like MPLS or something like that. So yeah, get VPN, quite popular still, and we need to spend some time on it. And then I will move on to the Flex VPN, but before I go into that, I need to spend some time talking about IGV2. Okay, so the theory behind the IGV2, what it is, how it works, is it better, really better than IGV1? What are the new things, and how packets are being exchanged and so on. So we will talk about this because that's the prerequisite, because Flex VPN is basically based on IGV2. Right, so we'll then move to the Flex VPN, and I hope we'll have enough time today to cover all those things. One more thing, I would like to also talk about virtualization and something called a VRF aware IPsec. Aware IPsec. So I will just put that topic somewhere in between here, probably between DMVPN and GetVPN, but we'll see. Okay, so one more thing, apologize for last week late notice about the class. I had some health issues and I couldn't start the class and I just realized that like an hour before the class that I will not be able to teach. So sorry again about that. But something like that happens from time to time. So apologize again. Okay, guys, so let's move on and talk about the MTU in a DMVPN, MTU role in a DMVPN. Okay, so a typical DMVPN deployment, when we talk about DMVPN or generally about any GRE over IPsec, it's not only DMVPN, it's basically any GRE over IPsec. Whenever you use tunnel, you need to do something with the MTU because that's not gonna work sooner or later. Okay, what's the problem? When you have a router, let's say two routers on both ends, and you build a tunnel between them like this, not really nice tunnel, but and you have a tunnel between them, tunnel 0 interface here, tunnel 0 interface on the right. This is a GRE over IPsec. All right, so remember, when it comes to the data encapsulation, you will have some additional headers added to the original packet, right? It's actually 24 bits for GRE and IP address, IP headers are added by the GRE. That's for the point-to-point GRE, or 28 even for MGRE. So MGRE plus IP. That's going to be 28 bytes in addition to the normal packet. So let's say you have a host here on the left and host on the right. If you are sending a packet, we always talking about something called an MTU, right? We have MTU, the default MTU in Ethernet is 1500, right? Oh, sorry, no audio. Hey guys, can you hear me? Okay. Okay, so something's wrong with the audio for one person. Okay, move on. So MTU 1500, right? And we usually, that's a default. So if a host is going to send some data out, the data in the packet cannot be bigger than 1500. It actually, the whole packet cannot be bigger than 1500, right? So it's usually the maximum segment is 1460, which is 40 bytes less than the MTU, because you have some additional headers here. IP header, which is 20 bytes, right? And you have some layer 2 header, which is another couple of bytes, and the TCP or UDP header, which some additional bytes as well. So the default is actually this behavior when the data in the packet maximum size, or this we call it MSS, maximum segment size for data is 1460, 40 bytes less than the MTU. Okay, and now when this packet is sent over the tunnel, right, in here, if a tunnel has MTU of the default MTU on the interface is obviously 1500, but it's minus 24 or even 28, right? In point-to-point, that's going to be 24. So actual MTU available on the tunnel, point-to-point tunnel, is 1476, if I calculate that. That's a good way. So MTU on tunnels, right? So our packet will not fit this MTU. and must be fragmented to 2 packets, right? So there are going to be 2 packets instead of 1. Okay, and there is always a case that when you fragment the packet, the defragmentation of that packet is done by the destination host. It's always the case that destination host must defragment, not the router on the right. Okay, the destination host itself. Let me put that. Destination host must defragment. Okay, so yeah, we are increasing the load on the destination host because of that. That's why. So what's the issue really? If you have such scenario, you will not see the issue if you have any issue if you have small packets. But if you have big packets, like maybe HTTP traffic or FTP traffic, when we have, you know, full packets, like the full payload is being sent, then the fragmentation and the defragmentation on the other end will decrease the speed of the link, right? So from the end user, the experience is really bad. End user says, okay, something's wrong with my network. It's slacking. It's not fast enough. It was good, but once they implemented this DMVPN, it started working, you know, slower, right? Yeah, the host is busy with doing the unnecessary thing, which is the fragmentation, and this router is busy because it must fragment the packets. Right, so the overall there is a bad experience, and it's slowing the network. Okay, so that's the issue that we need to deal with. So how we can deal with that? There are 2 ways to do this. The best way to do that is something called, we can use MSS adjustment. MSS is maximum segment size. Right, and the maximum segment size is actually this, right? It's 40 bytes less than the actual MTU. So how we can use this information, how we can adjust this? Because on the interface tunnel, let me put config here. We have IP address, obviously, the tunnel source, tunnel destination, right, for point-to-point. We have some tunnel mode, which is a GRE or GRE multi-point, right? And in case of DMVPN, we usually configure 2 things. One is IP TCP adjust MSS command. One is IP MTU. Those 2, okay? We are adjusting MSS to usually to 40 bytes less than the actual MTU on the interface. So that's done automatically. If the MTU is 1500, we have 1476. But it is a good practice to lower the MTU on the tunnel interface to 1400 instead of the default 1476, and to lower the MSS to 40 bytes less, which is 1360. Okay, so this is 40 bytes less than MTU. Okay, why we doing this? So how adjust MSS works? Okay, let me put the topology real quick. So again, we have a client here. We have a first router, then we have some router, another router, and the destination host, the server. there's a question in chat. Even if IPsec is not enabled, you mean if the TC adjusting MSS works if there is no IPsec? Yes. Yeah. But if you don't have IPsec, you still have those 24 bytes less. But the router, the default, even if you don't apply IPsec on a tunnel, you will have this MTU lower because of GRE, right? I didn't added any ESP here, right? So it's just GRE part plus ESP. It's even more, right? Yeah, I will be talking about UDP because we cannot do two things, those things with UDP, because that works only for TCP, as you see in the command. Okay, so see this. Let's say we have a 1500 MTU here on the segment where this host is, the client. Then we have something that will decrease the MTU, for example, tunnel with the IP MTU command, or just the interface with IP MTU command, right? So 1400 is here, 1400 is here, and here we have 1500 again on the server side, right? Here we also may have 1400. Doesn't really matter, okay? Now, this command works this way so that when we have it configured on this router on the outgoing interface, in a TCP SYN packet, we're gonna be MSS, maximum segment size field, set to 1460, and this is default. Again, 40 bytes less than MTU, right? And this router, having this command configured, may adjust this to MSS configured with a command. In our case, 1360, right? This is still TCP SYN. Anything else is not changed, just the MSS field in the TCP packet. Once it hits the server says, okay, I'm gonna be using 3060 maximum segment size when I will be sending packets to the client, right? So server will decrease number of data, or amount of data rather, in the packets that are being sent back to the client. Okay, and same works in the opposite direction. In a TCP SYN ACK packet from the server back to the client, server says, okay, on my end, right, I can handle 1460, right, maximum segment size. And again, we need to change this in this packet, right, so that both knows about it. Okay, so after exchanging those two packets in the TCP through a handshake, we know, both ends know, that they need to decrease the amount of data in a single packet to 1360. So there will be no fragmentation along the path. Okay, so that's the ultimate solution. That's a great solution, and it works for TCP pretty well. The problem is, though, with a UDP, as someone asked in the chat. With UDP, we don't have three handshake, right? So they're gonna be, we don't have that command for UDP, so we cannot do anything here, except we could still do something with using maybe a route map. Okay, so for example, we will not let hosts using UDP to decrease maximum segment size. Okay, but with UDP, the problem might be that inside the packet there is a DF bit, don't fragment bit set. Okay, so let me put that maybe here on the slide. What to do with DF, don't fragment bit. Okay, so if the host is sending a packet 1500 with a DF bit set, then we cannot fragment that packet. So if we have 1400 here MTU, this packet will be dropped. Okay, so because the DF bit prevents this packet from being fragmented. So what we can do here, we can apply a route map, okay, with a clear DF option on the incoming interface, and then we can set MTU here to lower to fragment the packet. So packet will be fragmented. But this is not the solution to not fragment, right? It's going to be fragmented anyway. You could also ask that there is one additional thing called PMTUD. What is PMTUD? PMTUD is the Path MTU Discovery solution that should potentially tell us, or host, what is the recommended MTU along the path. It works with an ICMP packet. Right? So if you are this method or technology works this way. So this host is sending out a packet, with MTU 1500 and then DF set, and waits for a drop and ICMP packet saying that the MTU was exceeded. So there is an MTU message saying MTU exceeded, and inside this message there should be an information what is the recommended MTU. Okay, so if you have 1400 here, this router should drop the packet and send back information about with ICMP MTU exceeded, and this host can then lower the MTU and lower the maximum segment size as well. That may work also for UDP, but unfortunately, it may work in your network, but may not work over the internet. For example, because it's based on the ICMP, and the ICMP is sometimes blocked by some service providers. ICMP, I mean like MTU exceeded message code. Okay, let me check the chat. 2K. Okay, so that depends if answering the question in the chat about the 2K MTU. Was it on a host as well? I mean, the host has the 2K or just the router? Because if that's the Just the router, okay. So um, okay, yeah. So depends what was the configuration. If the configuration was to yeah, without adjusting MSS, it depends, right? If on the host there was 1500, then there shouldn't be any issue because it's lower than the 2K. But uh, yeah, so it had to be on, in a network, because I'm not sure about that. That would be something that I would need to see to tell you what's the issue. Hmm. Yeah, yeah, but one more thing about this PMTUD. This mechanism is from the security perspective, it's not very secure, because it's basically taking any ICMP packet, unsolicited, we call it, right? It's not authenticated in any way. You just can inject ICMP packet with MTU that send it to the router that supports PMTUD, and this router will decrease the MTU on an interface. I was testing this. I was attacking a router that was connected to the internet, having some tunnel, IPsec tunnel, and I sent just the injected packet with MTU like 500, and the router took that and decreased the MTU to 500 per my packet. So that's not really a good solution, especially on the internet edge. Right. So once again, lowering the MTU will not cause that there is no fragmentation, right? It's the opposite. It will cause the fragmentation. So, but we are decreasing the MTU in order to let other nodes that we have a lower MTU, and in order to do the fragmentation after encryption. By default, this is the case. The fragmentation is done before encryption. Sorry, yeah, that's the default, before encryption. So we are fragmenting clear packets and then encrypting them, right? So one clear packet on the left gonna be resulting in two encrypted packets. Okay. There's also a way to change the configuration to fragment after encryption, which is really, really, really bad idea. Because if you do that, the other router on the other end would need to defragment before decrypting those packets. So that's gonna probably kill that router. All right, so that's not a good idea. The default is to fragment before encryption. Okay, and the default, and not the default, but the best practice, let's say, is this. This is the best practice. Okay, this, to add those two commands on the tunnel interface. Okay. Let's move on and talk a little bit about high availability in a DMVPN. Oh gosh, what's this? Clear before and after decryption. No, the default is to fragment before encrypting, right? So if we need to fragment the packet, then we are fragmenting the clear packet and then encrypting those two clear packets, fragmented packets. But the bad idea is to do opposite, is to encrypt the packet and then fragment this encrypted packet, right? Because in this case, the other router on the other end would need to first defragment and then decrypt the packet. Yeah. Okay. Okay. In case of high availability, as I said, we have usually deployments with only 2 hubs, but we can do that in many ways depending on how many links do we have, how many ISPs do we have, and so on. What is the best, or maybe the most common DMVPN use case today is to do a wide area network backup. Okay, that's the first thing. The next thing is to just encrypt your wide area network, whatever it is built from, right? Like MPLS based IPVPN, you want to encrypt that, you may use DMVPN for it. But the most common use case today for DMVPN is to provide a one backup over the internet. So let me put that on slide. So most common DMVPN use case today. Wide area network backup. Okay, which means that you have your regular wide area network, for example, MPLS based, right? And you build a backup for it over the internet. Right? So, and you need to obviously encrypt that. So you build a DMVPN over the internet, right? And connect your routers to that DMVPN cloud. So those routers may have 2 interfaces. One is towards the wide area network, one is towards the internet. Okay, and another trend today is that branches today have direct internet access. So that allows this kind of configuration. Branches today, right? They have DIA, we call it, direct internet access. So we can use that to build DMVPN backup to the one directly from, between all those routers. That's the one thing. Another thing is that we don't need to have centralized internet access anymore, right? Like it was a couple of years ago, was promoted to have only one internet access at the headquarters, and then all we are utilizing the wide area network from branches to reach out to the internet through the centralized internet access. Today, since we have that direct internet access anyway, it would be better even to go directly to the internet rather than utilizing this wide area network, which is quite expensive, right? But from the other hand, when you take a look at this, that's going to require you to spend some money, additional money on securing this, because that direct internet access must be secure as well, secured somehow. Right, so you can think about putting a firewalls, but maybe instead of putting 100 firewalls, if you have 100 branches, maybe you can go for something else. That's why today it's quite popular, I would say, but maybe not yet that popular. But it's trending to use security in the cloud, right? Cloud security, like umbrella, like even the not routers as well, but even the firewalls can be now deployed from the cloud. So you don't need to have that firewall locally. You may have it in the cloud and manage it from the cloud. All right, so that's a common. So from the high availability perspective, you need to know that there is no DMVPN deployment with only one hub, right? We always have at least two. And that's also maximum sometimes, because there is no need for more deployment. Right. So if we have two hubs, and depending on how many links or interfaces we have, physical interfaces, we can have that in the single cloud deployment or dual cloud deployment. Let's start with a single. So we call it dual hub, single cloud. That's the quite common, but we'll see. So in this case, let's say that's the internet, and we build that DMVPN over the internet. We have two hubs, 1, 2, right? Hub 1, hub 2. And we have spokes. So I have a spoke 1, I have a spoke 2, and some networks behind them. Behind the hubs, we have one common network, usually. I see that in the chat. Yes, sure, Raminder. Yeah, Raminder is asking about two ISPs links. Sure, I can do that. So obviously we are all connected to that internet, right? And now we build a DMVPN over it. So how we can build that? We are configuring the tunnel interfaces, right? And what? And we are registering to that tunnel interface, right? From one spoke, but we also register to another hub, like this. Okay? How is it possible? If we have interface tunnel on spokes, interface tunnel, we're just configuring IP, NHRP, NHS twice. NHS, it's the next hop server, right? 172.16.1.1 and IP, NHRP, NHS 172.16.1.2. Notice that it's still the same network, right? I mean the same network subnet. And the same thing on the spoke 2, right? We are building tunnel interface and we are registering to hub 1 and hub 2 at the same time. So this is not a kind of primary, secondary. It's just when we configure that on the spoke will register to both hubs at the same time, which means both tunnels will be up. Okay, it's a still tunnel 0 interface, right? But we have like two paths over this tunnel 0 because that's the multi-point interface, remember? Right? So this is quite good approach. The problem that I don't like this is that it's hard uh, to do traffic kind of to tell which path is the primary, right? It's hard with that deployment. It requires us to do some additional configuration with the routing protocol over the tunnel in order to do the traffic engineering. Right? So for example, in case of the ERGRP, right, we need to use delay to do traffic engineering. Right? For example, I say on this interface, tunnel interface, I configure delay to 1000. On this, I configure delay of 2000. Right? So in this case, when a spoke tries to reach out to the hub, it will choose this path, the path on the left, right? The path on the right will be worse. The problem is in the opposite side, because now when someone from this network on the top behind hubs wants to reach out to the spoke 1, now we need also tell this guy which path is better. So is it hub 1 better or hub 2 better? Right? So we need to again configure ERGRP delay so that this path will be preferred to have kind of symmetry in the traffic. Okay, so it's a little bit more complicated. It's not done automatically. We need to adjust something in the routing protocol to tell which path is the preferred one, unless you don't want to do anything with it. And if you don't do that, that might be that the asymmetry, right? So for example, the left path will be taken from the spoke to the hub, but from the hub's network, the hub 2 will be chosen, and the cross tunnel will be used for the returning traffic. Right? It's still gonna work, but it may cause some out of order packets sometimes, right? Because there's always something. If you use some traffic load, or not load, but load balancing, there's always a chance of out of order packets. Can we use SHRP on the HQ LAN and provide VIP as hub 1? We could, yes. We could. But then you need to connect those two and enable ERGRP on that link between hubs, right? In order to, in case of some, a failure, it must, switch to hub 2 and to other path. But yeah, that's possible, obviously. Okay, I'm a big fan of simple solutions. Okay, because people have tendency for doing some redundancy of redundancy, like configuring things which may work well at the beginning, but they are trying to solve something that may not even happen in the future, right? So the simpler solution is better, I think, in my opinion. Okay, so what if we have two ISPs? So I will be talking about single hub, dual cloud. It doesn't mean that there is no redundancy because there is a single hub. Actually, because there are two clouds, there are still two hubs. Okay. So in this case, notice the following scenario. We have two hubs. They are still connected to the same network behind them. We have some network, common network, and spokes. But this time, we are building two DMVPN clouds. This one, the red one. So both spokes will be talking to the hub 1 through this red cloud, and a blue cloud for another hub, another spoke. So notice on the spoke now we have two interfaces, two tunnel interfaces, not one. And in this case, it is easier to do traffic engineering from the spokes perspective, right? Because we have two separate interfaces, so it's easier to choose one than the other. Okay, what is the spokes config? We have interface tunnel 1, let's say, IP NHRP RP NHS 172.16.1.1, and the tunnel source geek1. Okay, the tunnel source for the red tunnel. And another one, interface tunnel 2, IP NHRP, and we are registering to the NHS from a different cloud, which means there is a different network subnet. So let's say 2 at 1. And the tunnel source gonna be different physical interface. And that should tell you what is the single hub dual cloud for. It's because, so this is cloud 1, this is cloud 2. Right? It's a very common scenario when you have dual ISP. Right, so a single router is connected with two interfaces to two different ISPs, ISP1 and ISP2. If those ISPs are connected to the same network, that's even better, right? But that's not always the case. You may have, if that network underneath, it's not the internet, but you have two ISPs that are providing your MPLS based wide area network, right? Then those are two different ISPs, two different networks, right? So you have no choice rather than building dual cloud. You need to have one cloud per ISP1, another cloud per ISP2. It's a different case if your ISPs are providing you just the internet access. Then they both providing you access to the same underlying network, right, to the internet. Then it's a little bit different. Then you can even build a dual hub, single cloud. You don't need to do dual cloud in this case. Still can, but you know. So in the classic DMVPN, that's important. In the classic DMVPN, you must configure two DMVPN clouds to support two ISPs if they are providing you different networks, not the internet, okay? So in classic, we call it classic DMVPN, okay, because the classic DMVPN is not flex mesh, right? Because with a flex, you don't need to do that. With a flex, you have some abilities to build, to utilize two ISPs with only one cloud. Two DMVPN clouds to support two ISPs. Okay, the question in the chat, what if my hubs are in a different location? For example, I have a hub in north and another in south, and I want all the sites to the north should use north as primary, but if that fails, should go to south hub. Okay, with a classic DMVPN, when you are configuring dual hub, both hubs will be, or spokes will be connected to both hubs at the same time. So you can do that, but you need to do traffic engineering. So say the delay is better, lower on the primary link to the north, and when the hub on the north dies, then it's gonna move to the south. So I would go in this case for the previous scenario, unless you have two ISPs. Is it? I believe this is through internet, but is it? There are two ISPs. Okay, but two ISPs to the internet. Yes. Okay. So in this case, I would go for a previous scenario. So dual hub, single cloud. Right, with some traffic engineering on top of that, with the routing. Okay. So some people are crazy and they are doing things like I said, this is a redundancy of redundancy, I call it. It's a dual hub, dual cloud. Right. So in this case, you're gonna have something like this. You have two hubs, two spokes, and then they are connected to two different ISPs, and you do something like this. You're building one network like that. From the other spoke, you're connecting to the same cloud, to the red cloud, and then you're building the same for blue cloud. So creating another cloud on the same routers, right? So other tunnel interfaces. Then you have kind of totally active, you might be active standby if you, in case of two ISPs. But as I said, this might be the reason or the case when you have two ISPs not for the internet. Right? So over one ISP, you're building this red cloud, on another ISP, you're building the blue cloud. But still, right, both routers are connected with two physical interfaces to two ISPs. Same here. And on the spoke is also connected here and here. And another spoke is connected to both ISPs as well. Right, so this is physical. This is logical. You can also do with a DMVPN phase 3, you can use a hierarchy. DMVPN phase 3 hierarchy. So for example, you may have one hub on North America and one hub in Europe, right? And then you're interconnecting those hubs. I'm not talking about physical connections, I'm talking about tunnels. And then you have, instead of spokes connected to those hubs, you are having another hubs. For example, another hub in California, one is in Florida, something like that. Okay, and those hubs are just connecting spokes like this. Same in EU, but instead of states, you have countries. So like let's say Germany, and you have France, right? Hub and spokes here. And the trick is that you would like to be having this. You have a spoke here and the route and the host behind it, and you have a spoke here and a host behind it. So it would be nice to have a direct spoke-to-spoke tunnel like this built between those. And this is possible. Okay, it's possible, but remember, in order to do redirection or trigger the redirection, you need to have the same network ID configured. So for example, in this case, on this interface, network ID should be 123 and it might be different here, might be 123 here. This can have 254, 255, whatever, right? The trick is that to have the same network ID on two interfaces on the same router, because network ID is the locally significant number. Remember, network ID from NHRP. Locally significant. Okay, but it triggers redirection. So if you have a data packet, let's say, data packet goes here. This is the first hub. If this hub knows that its locally significant number is 100, and it's on this interface and this interface towards another hub, right? Obviously, the data packet will go here, 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 and here to the destination based on the routing, but that will also cause the redirection. This hub will say, okay, you need to redirect. You need to ask me what is the better way to reach the destination. Okay, so they're gonna be the resolution request. The resolution request will be forwarded, and this guy will build a tunnel back to us. It's all because of the network ID, the same network ID on two interfaces, two or more interfaces on a single router. And I will show you that on in the lab in a second, because I was configuring this especially for you to see how it may work. So let me show you the lab topology. For DMVPN HA. So in my lab now I have this. I have two hubs, hub 1 and hub 2, and I have two spokes, right? The branches, branch 1 and branch 2. And what I configured I configure this way. Instead, for at least for now, okay, just to show you the importance of network ID. Instead of configuring dual hub single cloud, I did something like this. I created a tunnel between branch 1 and hub 1. And I also created a tunnel between branch 1 and hub 2. Okay, like this. And now there is also another interface, tunnel interface between them. This is tunnel 0, I believe, towards the spokes, and this is tunnel 100 between hubs. For now, I just disabled this tunnel interface. Physically, they are still connected. Okay, they are connected with a network behind them. Okay, so in this case, this is 192.168, I think 2.0. This is 3.0, and this is 1.0. Right. So let me show you without this tunnel 100 how it works. It still gonna work, but we will not have redirection. Let me show you that so you might better understand that. Let me share access. Oh, here. Okay, show run tunnel interface. Okay, interface tunnel 0. That's my tunnel 0 on the hub 1. That's the tunnel 0 on hub 2. Notice that I'm still in the same network, 172.16. This is 1.1 hub, 110 is the second hub. The whole configuration is exactly the same, except the network ID is different. But remember, network ID is locally significant. Right, so on the branch 1, show run interface tunnel 0, I have only one NHS configured, which is this guy here, right? Hub number 1. On branch 2, I have another NHS configured. See, this is the hub 2, 1.10. Not this one, this network, this command. Right? So I'm connected to 2 separate hubs. Okay? Is it something bad or something that may not work? No, because the thing is to have a connectivity, secure connectivity, right? So notice this. If I do show, let me do show the VPN, so you see that okay, I'm connected to one hub. If I do show the VPN here, I'm connected. The one spoke is connected to me, right? If I do show IP interface brief, let me check if I have. Yeah, that's the 2.2. Show IP interface brief. That's the 3.3. Okay. Let me check the crypto. Show crypto IPsec SA. Encryption, decryption. Okay, I see some packets are going through ERGRP, right? Hellos. Same here. One tunnel towards the hub. One hub is 192.0.2.20. One is 192.0.2.21. Okay. If I do show IP route 192.168, oh, show IP Ceph. 192.168 3.3 tells me that okay, I need to go through the physical interface. Show IP route. Okay, that's not good because I don't have a routing. Notice show IP route ERGRP. See, I just see the interface, oh sorry, the network behind the hub. Right, so I see the network 110. I don't see the network 30 on branch 1. So that's because I don't have ERGRP. I don't have ERGRP on this interface here. I will add ERGRP, but instead of adding this directly on this interface, I will add this tunnels 100. Show run interface tunnel 100. So this is just a point-to-point tunnel. Okay, if I do show IP, yeah, show run section router. Yeah, this is 100. I have ERGRP over this tunnel, but this tunnel is not now down. But you know what? Let me do this. Interface tunnel 100. I will get rid of NHRP commands. Okay, and do no shut. So this is just pure point-to-point tunnel between two routers. I will do the same here. Just to let you know. Interface tunnel 100. Okay, ERGRP should be up. And now I should have network 30 visible. Okay, it's still visible through the hub. Likewise, on branch 2, I have network 20 still behind, and now behind the hub 2. Right? So again, ERGRP is running here, here, and here on those tunnels. Since the tunnel 100 is just a point-to-point tunnel, not DMVPN related, let's say. Okay, let me try to ping from 20 to 30. Ping 192.168, 33. Sourcing from loopback 192 and repeat 100 packets. Do I see anything in crypto? I don't see any point-to-point tunnel built. Sorry, spoke-to-spoke tunnel. I mean, I want to build this tunnel between them, right? All packets went through, but they went through hub 1, through the tunnel 100 to hub 2, and hub 2 delivered the traffic to 30 network, and in the opposite direction as well. Right? So from the data perspective, it still works, but this is not DMVPN. DMVPN is all about building this point-to-point on-demand. Sorry, not point-to-point. Right. I mean spoke-to-spoke on-demand tunnel between spokes. Right. So I will add, and why this is not happening? Simply because this router, this hub 1, is not sending any redirection back to the branch 1 spoke. In order to hub 1 to send the redirection message, NHRP redirection, I would need to have here on both tunnels the same network ID. Let me show you that. Show run tunnel 0, interface tunnel 0. network ID is 123. Okay? So I will go to the interface tunnel 100 and configure the same thing. IP network ID 123 and redirect. Okay. Same on the router 2. Show run interface tunnel 0. Here I have network ID 666. Completely different. And again, this is locally significant. So if I go and configure the same on interface tunnel 100, okay, let me do debug NHRP packet. And ping again. Notice that now I built additional tunnel between spokes. And see what happened on the hub. See, send traffic indication, sorry, but that's the redirect, right? Redirection. So router 1 is now sending the packet redirection, NHRP redirection. And thanks for NHRP network ID. Okay, here, network ID must be the same. And same here, must be the same. On tunnel 0 and tunnel 100. That will cause the redirection and will allow those two spokes to build a direct spoke-to-spoke tunnel between them. Right? Yes, obviously, if hub 2 or hub 1 goes down, right, we screwed because we don't have any other connection to the other hub. So that's obviously not a good topology from the high availability perspective. A good question. Obviously, it's just a topology to show you the importance of network ID. Okay. So I will configure that as it should be. Right? I will reconfigure it. So it should be configured in my case this way. I should have one tunnel interface here and two hubs configured, NHS configured on one spoke, on one branch, and on another branch I should register to both as well, like this. Then I will have redundancy, and I don't need to have this direct spoke to spoke, hub to hub tunnel anymore in this case, right? Because if I send the traffic this way, unless, okay, might be the case that the data packet will go this way, and that's something that you need to consider. It might go this way, the data packet, and instead of going this way, because the routing may be worse here, or maybe this, for some reason, this tunnel is not up, but hard to believe. It may go this way and this way, right? If that's the case, in order to build direct spoke to spoke, you need to have tunnel interface or direct point to point tunnel interface between hubs in order to do redirection. So it's better to have it, I believe. Anyway, right? So let's do that. Let's reconfigure it. So I will get rid of my, in this case, tunnel 100. We'll do no interface tunnel 100. Same here. No interface tunnel 100. Okay, and on the branch, show run interface tunnel 0. I will configure another NHS to register to another NHS. Take that from here, right? I need to do those two things. Oh, here we go. See, another tunnel. I need to have right. To hub number 2. Okay, so it all depends. Now I have traffic load balancing, right? It's we call it equal cost multipath, or right, and it's by default load balanced per session. That means it's not a packet per packet load balancing, it's balancing per session. So each session will always choose one of those hubs, okay? But we never know. If you want to change that, we would need to change the delay on the interfaces. So for example, on the interface on hub 1, tunnel 0, IP, I will just send delay 1000. And on this guy, delay 2000. Okay, see? Now 30 is available through hub 1. And here is also 20 is available through hub 1. So hub 1 is the preferred one. But from here, I will not see that. Show IP route ERGRP. Route 2 is available through 2 and 3 through 3 because that's the directly connected. So I would need to have a router here behind those two hubs in order to see on this router which one is the preferred path, right, to the destination behind the spoke. So now I don't have that load balancing, which is even better. If I do ping, it was in the history, I think. Oh, let me check the. Okay, 2 tunnels towards hubs only, and sending packets. And now I have the third tunnel between spokes. So now this packet should all go through the spoke-to-spoke tunnel. Okay, for me that's the most simple scenario, and that works great. This scenario, I mean, right? It's easy to steer the traffic, to do the traffic engineering, relatively easy depending on the routing protocol, and it's quite simple. You have a high availability. If hop 1 dies, let's do this. So for example, config interface tunnel 0 shut. So hop 1 died. Where's my show IP here? GRP. Okay, so nothing happened really. Notice that nothing happened because I have the next hop override, because I have a default, direct spoke-to-spoke tunnel. So it's still using direct spoke-to-spoke, and it's not affecting anything, right? I'm not affected. But eventually it should go down and point to the direct to another hub to reach out to, because this hub on the left that I just disabled is not needed if we have, since we have this direct spoke-to-spoke tunnel, right? We would need to wait for this direct spoke-to-spoke tunnel to die in order to see that the second hub is taking care of building the spoke-to-spoke, the new spoke-to-spoke tunnel. Okay. So I think that's it for DMVPN. And what time is it? Yeah, so let's take a quick break, grab a coffee, and I will be talking about VRFs and VRF aware IPsec after that. And then we move to the Get VPN and then Flex VPN today. Okay, where's my minion? Okay, so coffee break for 15. See you there in 15. Okay, let's move on. So the next thing I wanted to talk about is the VRF aware IPsec and the virtualization in a DMVPN. So we can, using the multiple DMVPN clouds, we can virtualize our network underneath. Before I go into that scenario, let me talk a little bit about VRS, because maybe not all of you may know what a VRF is and how it works. So VRF is a virtual routing and forwarding. And we have two flavors of VRF. One is depending on what's your environment. If you are in enterprise, you may only know about something called a VRF Lite. If you are from the service provider environment, you know about full VRFs support in the service provider environment, and then service providers using VRFs to segment their network so they can support multiple class customers. Basically, a VRF is, if you take a look at the on the router, say this is a router, you can divide the router to different virtual routing tables. Those are not completely like multi-tenant environments, but at least from the segmentation perspective, you can divide your router to multiple routing tables, right? So you have you can create a VRF 1 and VRF or 2 VRFs, let's say, and what is left is always we call it GRT, the global routing table. So if you have a regular router, right, all your interfaces are in a global routing table, GRT only. And GRT is a global routing table. VRFs are separated. So let's say we have a VRF red where two interfaces like Geek 2 and Geek 3 will be assigned to that VRF, and we have a VRF blue, and we can assign some interfaces to that VRF so that no traffic can leak between interfaces. Like interface Geek 2 cannot talk to interface Geek 3 by default, right? Because both two interfaces are in two different VRFs, which means they are in two different routing tables, right? And you can still have some interface without any VRF configured on it. Then this interface is in a global routing table. How to create a VRF? You just say IP VRF in the global routing table and give it a name like IP VRF red. You go to the interfaces, Geek 2 in our case, and you apply or assign this interface to that VRF with a command IP VRF forwarding or just VRF forwarding, depending on the iOS platform. Ding red. That will move this interface from its default global routing table to the VRF red. That's why if you do this, you had this interface already configured with IP address, this IP address will be deleted or removed from the interface configuration, because now this interface should be created in a different routing table. Okay, and the Geek 3 IP VRF forwarding red. And then if you want to see the routing table, use show IP route command with a VRF name, VRF red. Okay, same for another VRF, IP VRF blue, interface Geek 4, IP VRF forwarding blue, and same for interface Geek 5. And you don't. You have your router divided to two VRFs plus global routing table. And this is a VRF Lite, so you don't need to configure under the VRF anything else really. I know some people are configuring route distinguisher, things like that, but that's not necessary for a VRF Lite. Okay, it's a full VRF configuration that it's out of scope for this course. Now, how we can use VRFs? So let me talk about some basic VRF usage. Let's say you have two routers. Right, with some networks. Let's say this is a network 10.1.1.0, 10.2.2.0. Normally, when you have those routers interconnected with some link, that's not a big deal. All those links are in the global routing table, right? But what if you have a need to build another network, let's say this red network, which is gonna be maybe with the same IP address even, 10.1.1.0, okay? And the red network here, 10.3.3.0, and you want to separate those networks. Normally you couldn't do this because the router will not allow you to configure another interface with the same IP address or with the IP address from the same subnet, right? Until you create a VRF or put that interface into a separate VRF, right? Then what you need to do, you can divide this link to maybe sub interfaces and create another link, like a logical link on it, that's going to be VRF in a VRF red. So this network red is completely separated from the black network, right? And another network blue can be configured the same way. Right? So what you can do from the configuration perspective, you can do interface geek1. Let's say this is geek1 physical interface, geek1. Right? And normally this IP address under geek1 is in a global routing table. But you go and configure interface geek1.10 sub interface, right? Encapsulation.1q10 and so on, and IP and you put that in a VRF red, and you have that separation now. And IP address can be the same even, because we can have overlapping IP addresses because we have now those two interfaces in a different routing table. geek1.20 IPVRF forwarding blue. Right? So you are virtualizing your network this way. And you're separating the traffic so that red network cannot talk to blue network anymore. Right? So VRF Lite is like a network virtualization, right? On a layer 3, you're using VRFs to virtualize. On a layer 2, you are using VLANs to virtualize, to separate one from the other. Okay. Now think about DMVPN. In a DMVPN, let me put that here. You can use this VRF, really clever. Let's say we have a big wide area network, IP VPN, right? MPLS based and so on. Now, what you need to do, or maybe let's say you have one network, which is this regular network, and spokes here and a hub, right? That works. And now you have a task from your manager saying, you know what, we are building another network, this red, and this, let's say this red network is somewhat restricted network. Okay. The thing is that to be compliant, we cannot merge those networks together. That traffic must be separated. How we can do that, right? So obviously we could go to our ISP and buy another IP VPN separated just for this red network, but that's going to be expensive. So what we can do instead, having DMVPN, we can build a DMVPN cloud, right? And connect our routers to that cloud. Okay? If there is a need for another network, let's say voice network, but we want to separate that network as well, we can build another cloud. Right? And connect our router to this blue network. Okay? Our black network we can left it in a GRT, or we can build another DMVPN cloud, right? And it can be a separated VRF or just a global routing table. Doesn't really matter, because global routing table is like a VRF, right? So how we can configure that? So let's say we have interface tunnel 1 for a black network. We put it in a IPVRF forwarding, let's say, data. That's a VRF data. Then we have a blue one. So another tunnel interface, tunnel 2. Okay, but this interface is gonna be a different DMVPN cloud. So that requires 3 interfaces on spokes, 3 interfaces on the hub. Right, and we put that in the red VRF. And same for the third interface for blue. That's pretty cool because we are utilizing one network, underneath, but on top of that, we are building separated networks for different VRFs and so on. So that's pretty cool and efficient from the cost perspective. Now, a little bit more about the tunnels and the VRF support on the tunnels, because there is some confusion usually about that. In the case of VRFs, we have 2 VRF types. Not talking about VRF Lite and full VRF. We have something called iVRF or inside VRF. And we have something called FVRF, which is a front door VRF. Okay, what we already seen is the iVRF when we are configuring tunnel 0 or tunnel 1 with IPVRF forwarding. Right? This command is configuring iVRF for us. Okay, what does it mean? It means that decrypted packets gonna go into this VRF. Packets go here. Okay, So when we get this packet over the interface tunnel, we decrypt the packet, and the decrypted packet will be in a VRF that we provided here. Right? Front door VRF is configured under the interface with a command tunnel VRF. Okay. What is that for? With this command, we configure a front door VRF. So encrypted packets come from here, from this VRF. Packets come from here. Example. Let's say I have a router and this is the connection to the internet. And I'm building this, let's say this is a DM VPN spoke. Okay, I'm building a tunnel like this. This is the tunnel 0. And I also have some Geek1, the internal interface that is gonna be connected here. So in this case, what I would configure, let's say the physical interface is Geek2. Okay. So normally I'm just configuring interface tunnel. Let's do this, maybe interface tunnel 0 with tunnel source, right? Geek2 in this case. Tunnel mode, right? Mode multi, because that's the DMVPN. And I'm configuring IP VRF forwarding to forward my decrypted packets to the blue VRF. Okay, and this is the iVRF. The same here in the interface Geek1 must be in the same VRF in order to make that work. Right? But what if, in my case, my Geek2 is also in a VRF? Okay, if my Geek2 is in the VRF, Geek2 is IP VRF forwarding red. Okay, I just missed the colors. Red. Right, I would need to add a tunnel VRF in command, because otherwise normally tunnel source is Geek2. So normally this is in a GRT, but now this is not in a GRT. It's in a VRF red. So I must have tunnel VRF command red. Okay, so this, and this are the front door FVRF. This and this are the iVRF. Right? So this red VRF, this one guy here, is the front door VRF. So encrypted packets comes to that VRF. If I have on the interface Geek2 VRF assigned, I must use tunnel VRF command, because the source of the tunnel is that interface. It must be in the same VRF. Okay, so sometimes that's important. So knowing that about different VRF types inside VRF and front door VRF, we can do a VRF leaking if we want to. There are a couple of ways to do that with tunnels, right? So if we have a router with two interfaces, and let's say gig 1, gig 2, and we have a red, this gig 1 is in the red, but gig 2 is in the blue, okay, we can do the leaking or connect those two VRFs together with a tunnel interface, right? Where the source of the tunnel will be the gig 1, the tunnel or the crypted packet, let's call it, not decrypted, but the inside VRF will be the blue, right? So how we can do that? Let's say interface gig 1 is IP VRF forwarding red, and we have another one, interface gig 2, IP VRF forwarding blue. Now I can create a tunnel, interface tunnel 0, right? Where the tunnel source gonna be in gig 2, for example. And since the gig 2 is in a VRF blue, I need to have tunnel VRF command, blue. That's my front door VRF, F VRF, and IP VRF forwarding red. That's the I VRF. And that's the virtual way of connecting two VRFs together. Okay. The old method of doing the same is to use the physical link. So I know such deployments when people had a router and with two interfaces. One interface was let's say gig 1 and gig 2. One was in a red network. One was in a blue. Right. So the easiest way to interconnect those two was like this. Just a link, physical link between those two interfaces. Okay, the more common today is a configuration called the VRF definition, depending on the platform. On the routers, usually have that configuration with tunnels or just linking with a static route. VRF definition is on a newer routers or with the switches, layer 3 switches. So you use VRF definitions plus something called the route targets. Targets for leaking. Number 4, you can use PBR also, policy-based routing, to do that. And 5, very popular, you can use static route especially with a global keyword. So if, for example, if your next hop is in a global network in a GRT, you can specify a global keyword with a static route, and then this packet will be using this route from the global routing table. Judith is asking, how are the inbound packets route back to a tunnel interface? Okay, you mean about number one with tunnels. Um, you mean from the IVRF to the tunnel? Yeah, based on the routing. So you just do the static route, right, to the tunnel interface. Instead of pointing to the next hop, you're just pointing to the tunnel 0, to the interface. Yeah. Okay, so that's just a general theory behind the VRFs, but the thing is that we need to know about how to configure VRF aware IPsec, because that's the thing that is might be quite difficult, because IPsec is a separate technology and it may not be aware by default about any VRFs, right? So if you have VRFs and if you have a crypto, you need to tell the crypto that it should be using the VRF. Everything is working fine except one thing. The problem with IPsec is with a pre-shared key. So by default, a pre-shared key configuration is available only for a global routing table. So we need to tell that this particular pre-shared key is not for a global routing table, is for a specific VRF. Okay? Everything else, any other IPsec configuration on the router is by default shared by the VRFs. Okay, so basically, if you're talking about VRF awareness of IPsec, is just one thing that you need to take care about, which is the pre-shared key. Actually, you can do that in two ways. You can do VRF aware key, pre-shared key, I mean. Let me put that, maybe that note by default. Pre-shared key config, right, with crypto isacamp key, right, this command is available for GRT. For a global routing table. Okay. If you want to make it available for something else, you need to do that with a crypto keyring. So you need to create a new construct. You need to use a different command. Crypto keyring, give it a name, and then you specify a VRF blue. That's gonna be for this VRF. This key will be used. And then you have a command pre-shared dash key Cisco 123 address, and you specify the IP address of your peer. Okay, that means the VRF. And optionally, something that is not very popular in a configuration, you can configure something called an ISACamp profile. Okay, guys, can you hear me well? Because Judith is having some issues. Okay. Yeah, so optionally, not very popular is ISACamp profile. Okay, MP profile. We're gonna be talking about profiles, but for IGV2. In IGV1, they are not very popular. Crypto ISACamp profile test, give it a name, okay, and you say match identity. The profile, what is this? The profile is basically, I like to call it a connection catcher. It's catching the connection. It's very important in IGV2. We'll be talking about this later today, but if you know maybe configuration of IPsec or crypto config on the ASA you have something called a tunnel group or connection profile. So basically, this tunnel group or connection profile is this connection catcher. It's something that is taking the connection from your peer and handling this connection. So exactly the same thing is the ISACamp profile on a router. Okay, its purpose is to match for something, to catch this connection, and we usually match for identity, like address of our peer. So our peer will put its ID in the ID payload of ISACamp negotiation, and based on this ID, we are catching this connection. And then we can specify, okay, that's gonna be for a VRF, okay, red, let's say, or maybe not, because that's the VRF blue. Okay, so let me put the blue. VRF blue, right? And the keyring to authenticate is test. That's the keyring that we defined, this one. And this must be the correct VRF in this case. But that's optional. It is enough to configure, just the crypto keyring, and that's it. It should be fine. Only if you're using ISACamp profile, you need to add this keyring to the profile, and you need to also make this profile a VRF aware by adding the VRF command to it. Okay, so this is the I VRF. This is also the I VRF. Okay, in case this is more complicated, in case when you have a front door VRF, right? So your crypto encrypted packets are coming through the VRF to you. Then you need to add a VRF command here, red, right here, to the ISACamp profile. And this is the F VRF. Very unlikely, but to have that. But in case you have it, then you need to specify that this ISACamp profile is for VRF red, like the incoming VRF, the front door VRF. Right, a little bit complicated here. Normally what you do is just number one, okay? Just configuring keyring, make it VRF aware for a blue VRF, and that's it, right? Only if you want to configure ISACAMP profile for some reason, then you need to add this additional configuration. You also need to make it VREF aware. Okay. Right. So the next thing I wanted to talk about today is the get VPN. So let's move on. And at least start talking about this. So get VPN, what does it mean? It's a group encrypted transport virtual private network. Group encrypted transport, VPN. What versions of iOS? Basically everything now. It's very common on all routers, get VPN. So what's the idea behind it? Someone thought that if we have a wide area network, MPLS based, right? And the only reason that we pay for that a lot of money, and we want to encrypt that. Right? Maybe instead of building some overlay network like DMVPN, maybe it is just enough to encrypt that traffic, right? Let's take a look at this from a DMVPN overlay perspective, right? So overlay, we have what do we have here? We have by default any-to-any connectivity in that network, right? Provided by the service provider. We can talk to anybody in this network. If we have third branch, we can still talk to all other branches in a any-to-any connectivity on a shortest path. Let's call it this way, even though it's not always true, but let's say it this way. And now on top of that, we are building another network, which is what? Which is DMVPN, right? So we are building on top of that another network. And so we are efficiently breaking this any-to-any connectivity. Okay, we still have the ability to build on-demand spoke-to-spoke tunnel, okay, if needed. But by default, we are building a network on top of something that was really cool, but unfortunately didn't provide encryption for us, right? So DMVPN overlay is breaking any-to-any connectivity. Okay, it provides delays. Okay, because there is a delay because we need to build this spoke-to-spoke tunnel first in order to send the traffic between spokes directly. Okay, there's also a jitter, which is the problem, especially in a voice or video. If this guy wants to call this guy, first packets will go through the hub, and then eventually, after building this spoke-to-spoke tunnel, the rest of the packets will switch to the shorter path, right? So there's gonna be a jitter. Jitter means that those packets are having a shorter path, and there is a kind of fluctuancy between, packets. Not good in a voice or video. So someone thought, okay, maybe instead of doing this in case of wide area networks, I mean, not the internet, but wide area networks, maybe let's do that in a different way, because anyways, our goal is to encrypt everything that is going through this network. So maybe instead of building a network on top of that, we just encrypt everything that is going to enter this network and decrypt what is leaving this network. Wasn't that, simpler? The answer is yes. Obviously, it's very simple, but the problem is that the IPsec by nature is point to point. It must negotiate a tunnel between each peer. Okay, so it's not by default possible to just, we are sending some traffic from 10.1.1.0 network to 10.2.2.0 network, and we are encrypting this traffic this way, right? We need to first build a tunnel in a DMVPN in IPsec and then encrypt, right? So that's not a trivial task, but someone said, yeah, okay, but what if, since all those routers must share the encryption decryption policy, maybe we put something in the network that will tell those routers what to do and how to encrypt decrypt packets. So those routers will not be, needing to build or negotiate any tunnel between them. They are just, encrypting traffic. We will tell them what is the encryption key, and we will tell them what to encrypt and how. And that's it, right? So that's the get VPN idea, to pre-populate everything that is needed for data encryption, right, to those routers. And we do that with the help of a key server, KS, key server. So the key server is a router that is designated to be someone who tells us what to do. Okay, so all routers that are going to encrypt traffic will reach out to this key server, okay, in the registration process. So they need to do a registration first. Registration. In order to get a policy for data encryption. Those routers who will be doing the data encryption, we call them GMs, group members. And that's a group member. Okay, so the thing is that the key server delivers policy to other routers, to the group members. Delivers, let's say, data encryption policy to GMs. Okay, what is the policy? It's about what to encrypt, which is basically our crypto ACL, right? Crypto ACL, and how to encrypt, which is the algorithm, right? Plus key. So algorithm like AES, right? Plus key something. Actually, we call this key, I will tell you that now, tech. transport encryption key. Okay, so from the router's configuration, the crypto ACL is just a crypto ACL, and how to encrypt the algorithm and the key is just a transform set. Okay, so we are not building any tunnels, like we are not negotiating any tunnels between group members. We are just getting everything on the plate, and we installing in our IPsec SA, and we start encrypting traffic. Okay, without building any overlay. That's important. We are not using tunnel interfaces here. The basic idea is to encrypt something that, or everything that is going into this wide area network, decrypt what is leaving from that network. The problem is that notice that all group members must have the same encryption decryption key at the same time, right? Because what if something was encrypted with that key, it must be decrypted with the same key. So the key server is taking care of that. Yeah, so Niket is asking a very interesting question about what about the security of the key server, and if that's the so important thing and manages everything, what can go wrong, right? So obviously there is not only one key server. That's the first thing. From the HA perspective, we usually have up to 8 key servers. I know deployments where we have even more, even though it's not supported. 8 are supported by default. And even if you hack the key server, you will not see this encryption key, okay? Because the encryption key is hidden. So the same way, like if you go to the router and try to see the encryption key that you're using, that the router is using for the data right now, it's not possible to see it. So same here. Yeah, sure. Good question. Thanks. Okay, so you see the general idea is to encrypt everything that is going to the Y1 or a network and decrypt what is leaving the network. So let's take a look at the key server first. KS. So the key server is just a router. Okay. But the best practice and the recommendation is to have it as a separate router. So the key server is usually not the group member. Okay. Simply because we don't want to overwhelm the key server with any other activities. So the key server is just a separate router. Does it has to be out of data plane? It's actually the control plane activity the key server does, but yes, yeah. The short answer is yes. It should be out of the data plane. Right, and its role is to tell other routers or GMs, right, what to secure and how. Right, what to secure is the crypto ACL that we configure on the router. How to secure is the encryption algorithm that we define in the transform set, and the encryption key. Right, that we call tag. Transport encryption key. Transport encryption key. Okay. Also, it's taking care of registration, so registers GMs, and also very important, it's updating the tag. Yeah. Right. So registration is the registers GM is the registration phase, and updating the tag, because again, if we want to have a secure encrypted traffic, we need to change the encryption key from time to time. Right? By default, in point-to-point IPsec, we change the encryption key every 1 hour. This is the lifetime of the IPsec SA. Right? Same here. We call it rekeying. Right? So again, if we take a look at the operations, we have group members and we have a key server. So the registration is done from the group member to the key server. That's the registration. Okay, but the rekey is done in opposite direction. Because after 1 hour or 2 hours, or depending how you configure it, the key server must deliver a new encryption key to all group members. Right? So that's the very important aspect. I'm gonna talk about this in more details. Now, let's take a look at the registration first. So how group member registers to the key server. Okay, so registration. Again, registration is the group member link to the key server. Okay, it's done, believe me or not, with ISACamp. So ISACamp, but the difference is that instead of, from the packet perspective, instead of using UDP 500 like we do in IPsec, we use different port 848. Okay. Plus, obviously there is also something different inside the packet. So let me show you that. So if we compare ISACamp for IPsec, regular IPsec over UDP 500, right? We have phase 1 main mode, obviously, and the outcome of that phase 1 is the bidirectional ISACamp SA, right? The secure authenticated communication channel. Secure channel, right? Secure authenticated communication channel. Then we do phase 2. In this case, quick mode is the name of it. And the outcome of phase 2 are actually 2 unidirectional IPsec SAs, right? Our data channels. right? Unidirectional. Right, so when you compare that to the ISACAMP for get VPN, it's quite similar. Again, UDP 848, the port is different. That's the first difference. We have also phase 1, main mode. And the purpose of the phase 1 is exactly the same as it is for IPsec, is to build ISACAMP SA, our secure authenticated communication channel between group members and the key server. Once we're done with this, the phase 2 is different. Instead of negotiating data channels, right, for data encryption, we are doing registration. We call it the phase 2, we call it GDOI, Group Domain of Interpretation. That's the name of it. And the outcome of phase 2 is, again, two unidirectional data channels, data encryption channels, that's going to be delivered to the group member. That's the registration. That's a registration. The difference is that, remember, in case of IPsec, those two unidirectional IPsec channels have a different SPI number. Right? 1, 2, 3, 4, 5, 6. Right? So SPIs are different. In case of get VPN, those SPIs are the same. And I will show you that in a configuration. Why SPIs are the same? Because there is no, we are not building any or negotiating any data channels between peers. We are just delivering to the peers information how to encrypt packets and what SPIs we can use. And all routers, all group members will share the same information. They're gonna get the same data channels, like pre-configured, right? What to secure and how, with a tag, with a transport encryption key, and the same SPI number, so that when one router, one group member is encrypting traffic, the ESP packet will be with SPI 123 sent to another group member, and no matter what the group member is, this group member will be ready to take the SPI 123 packet and decrypt it. Okay, so this is the common shared data encryption policy. So I cannot show you this. Actually, I have this registration in the Wireshark, but I cannot show you that because it's encrypted anyway, so it's gonna be hard, but at least let me try to find it. And Okay, notice this. This is the ISACAMP, but notice the port 848, right? And we have, even though the interpretation of a Wireshark is wrong, because we first have 6 packets for the main mode, which is okay, but then notice this, the quick mode, 4 packets. The quick mode is 3 packets normally, right? This is because the Wireshark get it wrong. It says this is the quick mode, but this is the GTOI, really, the registration. So if you compare that again to this, phase 1 is 6 packets, phase 2 is 3 packets for the regular IPsec. For GetVPN, phase 1 is still 6 packets because that's exactly the same thing. And phase 2 are 4 packets, the registration. Okay, so notice that this is exactly the same thing. We are negotiating the security association, we are building the tunnel, we are sending the key exchange, the Diffie-Hellman stuff, then we are authenticating the identity, and we're done. And then the quick mode, and see the encrypted data, so because that's not visible. But this is the registration over the different port. So phase 1 is exactly the same as it was for IPsec. Phase 2 is different. Okay, so what will happen with that registration for packets? Again, put that on the one slide. So group member to the key server, right? Over ISACAMP UDP 848. That's the transport. We are sending in those 4 messages crypto ACL again, the transform set, so encryption algorithm and protocol encryption algorithm. Transform set, encryption key, tech. By the way, this encryption key is not negotiated in any way, like it is normally. It's generated per session with IPsec, that key material. Remember that? So that's the encryption key in a regular IPsec. In this case, this tag is just randomly generated by the key server. And all group members will use it. Then, in addition to that, so again, group member to the key server, let's put it this way. We are sending, the key server is sending something called a pseudotime. Pseudotime. This is because they need to synchronize their watches, okay, clocks. We are not relying on the NTP here. The group member and the key server must synchronize their clocks with a pseudotime. This is very important because the key server, when it comes to the rekey, must change the encryption key on time. Right, so that's why that's quite important, and they do that anyway every 2 hours by default. So even if we don't want to do the rekey, let's say maybe we created or set the configuration that the encryption key is valid for 8 hours, the rekey will still be done every 2 hours because of this pseudotime, because of this synchronization. And another thing that the key server is sending in the registration is the key server's public key. We'll talk about this why in a second, why this public key is so important. And finally, the KEK, key key, the key encryption key. Strange name. So the key encryption key is gonna be the key encryption key used for the recce packet. Okay, so recce packets will be encrypted with this key. That's why group member must be ready with that key to decrypt the recce message. And then when it comes to recce, right, again, this time is the key server to the group member, right? First, the key server generates new tag. Right, let's say tag2, call it tag2. Second step is key server creates a new message about that new tag and encrypts this message with a KEK. Okay. 3, key server authenticates recce message with a signature. And the signature is done with a key server's private key. Right? So now you know why the key server public key must be delivered to the group member during the registration. Right? Based on this public key, the group member can validate that signature so that nobody else can, you know, deliver that message. It must be delivered by the key server that we registered to. And 4 is the key server delivers the message. To GMs. And there are 2 options here, or 2 ways to deliver the recce: unicast or multicast, where multicast is a default. Okay, so we're going to be talking about this after a break, how those 2 recces work. In my opinion, the unicast is better, even though the multicast is a default and multicast is recommended. But you'll see the differences between them, and I will tell you why the unicast is better in my opinion. Okay, what time is it? Let's take another quick break before I go into this. So we will talk about the recce, about key server redundancy, stuff like that, and then I will configure the group get VPN in the lab. So that's gonna be after the break. So let's take 15 again for coffee. Okay, see you there in 15. Okay, guys, let's move on and talk about the difference between unicast and multicast recce. So again, recce is from the key server to the group member. It's about changing the encryption key. And we have two ways of doing this, either unicast or multicast. So let's take a look at the unicast first, which is not the default. The default is multicast, but I'm going to show you what's the difference. So let's say this is a timeline for a lifetime of a tech. By default, we have a tech lifetime of a tech, which is 3,600 seconds, which is 1 hour. That's not going to be in the scale, but let's say by default in a 10% of tech lifetime, we start the recce phase. So in this case, that's going to be 360 seconds, right? Obviously not in scale, but I just wanted to show you this. So what will happen here? The key server will start sending the messages to each group member. So each group member must get a unicast message for a recce, okay, with having the new transport encryption key. And this message must be acknowledged. So there is an acknowledgement needed. Then the key server will not retransmit that packet. By default, there is a 1 packet plus 2 retransmissions. So if someone not acknowledged, then gonna be the packet recce packet sent out again. Okay, so if we have 1,000 group members, there are gonna be 1,000 packets. If everybody gets that, but if not, there may be more than 1 packets sent by the key server. And there is some time for that, because at the 5% of tech lifetime, right, we're gonna have a re-registration window started. So 180 seconds in this case. They're gonna be till 90 seconds. We're gonna have something called a re-registration window. So for those group members who are not getting or who did not get the original recce, those group members must try to register back to the key server. Okay, so only those group members who did not receive the recce message, right? So re-registration window is in this case that's gonna be 90 seconds, okay, for group members, and then 30 seconds is the time where we swapping tech, right? Techs. So basically, tech 2, the new tech, replaces tech 1, and 0 seconds, obviously, the tech expires, right? So old tech expires. So at 30 seconds before the original tech expires, we swap the techs so that all group members will start using the new tag, new encryption key. And we have still those 30 seconds window for any packets that could possibly be encrypted by the old tag, and they can still be decrypted. But all new packets will be encrypted with a new tag from 30 seconds. Okay, so if you take a look at the features of that, of the unicast recce, first off, it's a one packet sent per group member. Right, the acknowledgement process. If we have the one packet per group member, that means that the key server must keep a list of group members. Okay, and it's not a default. Okay, second is multicast. Multicast. So let's do the similar timeline. Again, at the 10% of tech, the whole process started. So the key server must deliver messages to the group members, right? The recce messages. But instead of sending individual packet to the group member, it's just sending a multicast, one packet to all group members. So group members need to wait for that message and listen for that packet. So one packet to a group like 239.10.1.1. Okay, so in the process of the registration, we tell that this is going to be the multicast transport, and then group members know what will be the group, multicast group that they should listen on in order to get that message. Okay. The rest of the process is pretty similar. So we have a 5% of tech. We have a re-registration window till 90 seconds. Okay, and then the swap and the expiration. Right. So what are the features of that transport? It's a one packet to multicast group. Right? There is no acknowledgement, no ACK. Once you get that, that's good. If you didn't, that's your problem. You need to re-register. Okay. And 2 retransmissions. By default. Okay. Okay, the problem is, and this is why I don't really like multicast transport for recce, is that it heavily relies on your network to be able to deliver multicast traffic. If there is an issue with a multicast traffic in your network, in the wide area network, remember, then none of the group member will get the recce message from the key server, and then they all will need to re-register. And re-registration, remember, registration is basically the ISACAMP, right? Registration is the ISACAMP. So the phase one and phase two. Phase one is the what? Is the authentication, is the Diffie-Hellman. So I don't know the numbers for other routers, but I remember from the past when if it comes to this 7200 series router, which is the old router but really cool. But you can basically take this knowledge and apply to newer routers as well. In case of new registrations, 7200 series router working as a key server, in case of pre-shared key authentication in ISACAMP phase 1, it can handle up to 100 registrations per second. Okay, so if you have 90-second re-registration window, we can support 9,000 registrations, right? More or less. But in case of RSA signature, so certificate authentication, it handles only 16 registration per second, which means in 90 seconds we have like maybe I don't know, 150 routers that can register with a certificate authentication. That's a big problem, and that was the problem in the past. Today it's not a big deal anymore because we have much faster routers like ASR 1000. That's a platform that we usually use for a key server. It's not that much of issue now, but it was in the past. So this re-registration window was the problem. And the multicast, that's why I don't like multicast, because it's heavily relies on the multicast underneath and multicast transport. By the way, it depends on the service provider. As I know, in US, most of the service providers for the wide area networks, they provide multicast support, but in Europe it's not that common actually, right? So it's not it's something that you need to additionally pay for. So for me, unicast is more reliable in this case, and today with ASR 1000 or similar platforms, it's not a big deal to send 1000 packets out, okay, or 2000 packets instead of 1 or 3. Yeah, so when you take a look at the designing of a Get VPN network, if the positioning of that is usually to protect wide area networks, right? Where the key server can be something like ASR 1000 or CSR 1000V, very popular, the virtual router that we use in the lab, or ISR G3 or G4, right? Those kind of things. For group members can be any routers, but any iOS router, including 800 series. So small routers, right? That just being on the one edge in branches, in our branches. Let's take a look at the data transport in Get VPN, because it's a little bit different than you know it from the regular IPsec. Right? In case of GetVPN, let's say we have two networks, 10.1.1.0, 10.2.2.0. So first off, both group members will register to the key server, registration. Then, once they get the whole policy, they just encrypting traffic between them. They use ESP as a transport, and they know how to encrypt traffic. Right. So if you take a look at the GetVPN encapsulation, okay, it looks like this. Let's say, based on our network, we have some data packet with original IP header 10.1.1.1 from host in this network to host in that network to 10.2.2.2. Right? Once this packet comes to the outgoing interface towards the wide area network, this packet is being encrypted with the ESP, encapsulated with the ESP, right, with a new header. And the new header has the same information that the inner header. So basically, all that information is being copied from the original data IP header. Okay, we call this, it's a tunnel mode, right? Because it works like a tunnel mode with IP header preservation. Okay, and also GetVPN is known as a tunnel-less technology. Because we don't have any GRE, right? So in case of GetVPN configuration, you must remember to have tunnel mode enabled, okay? Because the routing is based on the original IP header. We are just encrypting, encapsulating, authenticating the whole packet with the original IP header inside that packet. So this is the IP header preservation, including, so since we are copying the original IP header, we are including everything in there, including the QoS, like DSCP marking, right? DSCP or IP precedence, things like that. So that's really cool because we are basically routing this packet not by the additional routing protocol on the overlay anymore. We are just routing this packet natively in the using the routing that is working in the network underneath. That's very important to that. So that's why the GetVPN is basically positioned to encrypt wide area networks, and it's not really designed to encrypt anything over the internet. Okay, so GetVPN is for encrypting wide area network, not over the internet. Okay, last thing before we go into lab is about the key server redundancy. We usually don't have one key server because it's too important to just lost it. We usually have more than one. How many depends on the scale. We can have up to 8 key servers. Each key server can support group members registration. So the group member can register to key server number 1. This guy can register to this key server, or we can provide the redundancy so that if this key server is not available, we're gonna register to another key server like this. Okay, so the registration can be to any of these key servers. In case of redundancy, they all need to talk to each other. When the one is the designated primary, and we have secondaries. So all other key servers are secondaries, and they talk to each other with a special protocol designed for that by Cisco called COOP, Cooperative Protocol, OOP. It's a information sharing and synchronization protocol. Right, so what we are sharing, like for example, GM registration, right? So who registered where, and the policy, because all key servers must have the common policy. So tech must be the same, CAC must be the same, right? The access list, the crypto ACL, the transform set, and so on. Okay. Okay, so now a little bit of information here. GM can register to any of key servers. Okay, but it's very important. Recce is done only by the primary key server. So recce must be done by the primary. Okay, that's important information because remember, recce message is encrypted with CAC, but it's also authenticated with a signature. That's going to imply something. So recce is encrypted by CAC and authenticated with a signature. Remember, signature is done with a key server's private key. Right? It's a hash, some kind of hash, encrypted with a key server's private key. So that implies that all key servers must have the same key pair. Because if we now lost the primary key server and another key server becomes primary, another key server may have a different private key. But that this is not going to work, right? So that's very important that all key servers must have the same keeper. And that's very important, especially in the lab, in the CCIE lab, when you go there and they ask you to configure two key servers, you will need to have the same key pair. So when you generating the keys on one key server, you must make them exportable in order to export the private key and then import them on a secondary key server. Oh, I don't really, if get is on the CCIE, I think it was, check that real quick. Yeah, you might be right. The Flex DMVPN and exec tunnels high availability get is not there. Yes, that's right. That's good. One less. Yeah. So you must to make RSA keys exportable. Okay, let's take a look at the config. Okay, so instead in our lab, instead of configuring DMVPN, I'm gonna swap to get. So we have those branches. And our headquarters. By the way, they're connected this way to, we have ASA, and here is the router, and this router has two interfaces. It's the HQ router. Yeah, so I'm gonna configure the key server on this router and the group members on those two. All right, so we're gonna register to the key server. So this network gonna pretend this is the wide area network, even though it's not. Okay, so let's get rid of the config no interface tunnel 100. I got rid of that. Okay, so that's my key server. Crypto is just certificates and nothing else in a default configuration. Okay, so I need to deliver crypto access list, crypto ACL, and the crypto policy. So the transform set. So from the crypto ACL, I'm gonna create an access list. I'm gonna. It's a good practice to use the named access list. So IP access list, extended. Let's call it get. And I'm permitting what I would like to include. I can permit, let's say that 192.168.0.0 network. And permit, not this IP, from 192.168.0.0 to 192. Remember that there are wildcard masks on routers. Oh, that's gonna be my policy. Just checking one thing. Okay. So the main command is crypto GDOI group, and give it a name. This is a just locally significant name for a group on a key server. We call it get. The very important thing is the identity of the group, identity number, because that number is basically the number that must be in the registration packet, because we may have multiple groups configured on a key server, and my group member must tell to which group it wants to register to. So identity number is telling us this. And the server local, that's gonna change. Notice that the crypto GDOI is on, which means that the router started listening on port UDP 848. Okay, and what I need to configure here is basically my policy. So SA IPsec1. My policy gonna be the crypto ACL. So address. It's match, right? Match address. IPv4 and the name of my access list, get, and the profile, which is the IPsec profile I have a profile default because I'm using the default configuration here. But normally, if I don't have it, I need to create a crypto ISACamp profile with just some name, assign the transform set to that profile, and then this profile can be assigned here. For a recce, I would like to change the transport to unicast. Okay. And I need to specify the keys for a recce authentication. My public key, I think I have keys of a name keys, so I will, maybe not. Must be RSA, I think, RSA. Okay, I will show you the whole config in a second. Okay, and address that I'm listening on gonna be 192.0.2.20. What a second. IPv4, oh yeah, IPv4, 192.0.2.20. All right, so the whole config shall run section crypto GDOI is like this. Right, I have a local group. The identity number is 12345, and server local config is, this is the private key that's going to be used for recce, and the public key for registration. Transport is the unicast, and I'm going to provide the profile default, which is just the default IPsec transform set, and I'm matching, this is the crypto access list that I'm providing. Let me show you the show crypto IPsec profile default. Okay, so it's assigning the transform set of a name default with just AES and encryption and ESP transport. Okay, so that should be it on the server, on the key server. Now the group member. Same command, crypto GDOI group get. That's locally significant, so I can change this to whatever I want. Okay, I need to specify the identity that I would like to register to, and server, instead of server local, I just specify server address. I would like to register to the server of address 192.0.2.20. Okay, just those two things. And now I need to create a crypto map because it must be assigned to my interface. So crypto map, let's call it get. Remember, on the router we have a different crypto maps, so I'm gonna just assign some sequence number, and GDOI is the type of the crypto map. I need to specify it for the first time when I'm creating the crypto map. See that the note is that the crypto map will remain disabled until I configure valid group that I would like to register to. So set group get, that's my locally significant name of that group. And I need to go to my outgoing interface. Show IP interface brief, which is geek2 is my outgoing interface, and assign a crypto map to it. Okay. So something happened, as you can see. We have tech updated registration to key server complete for group get using this IP address. Right, installation of reg policies. All right, okay, that's good. So looks promising. Show run section crypt. That's my group config, so I can just copy that and paste on another branch. Crypto map gonna be exactly the same. Going to the interface and assigning it the crypto map to that interface. And same happened here. Obviously, authentication is done with a certificate, so it's done automatically for me. I don't need to do anything. If I do show crypto GDOI, there's nice command here, so let me show you that on one of those routers. Telling me that the group name that I registered it to is get. This is the identity of that group. Okay, the server is this. I have only one the key server configured. The group member is myself. Notice the port registered. Okay, and later I see the access list downloaded from the key server. Notice the access list is basically everything between 192.168 networks. The KEK policy. So what is the recce? Recce gonna be done with a unicast. Recce algorithm is 3DES. Okay, what else? And the SPI. Notice that the SPI number, it's only one SPI because, as I said, there is a common number for both SAs. So if I do show crypto IPsec SA, notice that that was injected to my IPsec config, this SA. So far, I don't have any packets encrypted, decrypted. So see that there is no peer because everybody in a group can be my peer. And see the SPIs, inbound SPI and outbound SPI. This is the same number. Okay, so if you do show crypto IPsec SA and you see the same SPI number in a SA, that should tell you that this is the get VPN delivered policy. See this. The SPI and the policy is exactly the same on both of these routers. See, SPI 703, 703, exactly the same. Okay, now I try to ping 192.168.2.2, sorry, 3.3, sourcing from loopback 192. Right, 3.3 is here, yeah. And notice that it doesn't work. How do you think? Why? Can I see any packets encrypted? Yeah, I see 5 packets being encrypted, sent out, but no packets decrypted. Question is, on the other end, do I see any packets decrypted? No. So it looks like the packets, encrypted packets from branch 1 didn't get to the branch 2. Right? mode. Yeah, it's related to the ESP mode. Remember, this is the IP header preservation. So we basically sending the packet as it is. We are not tunneling this packet anymore. Right? So that means this router in the middle, this router must know about those networks. Right? 3.0, sorry, this is 2.0, 2.0, 3.0. This router must know how to reach to those networks. We are not tunneling anymore. We are not using the outgoing, the public interfaces to tunnel. We are just sending packet out, and this router in the middle must know about the routing to those networks. Right. So what I can do to fix that, I would need to connect to that router, which is not that easy task, but I will try. I will do that from employee PC because it has a routing to the outgoing network probably. So should be able to reach out to that router. Oh, really? Okay, can't. Okay, it's using some old SSH version. Oh, gosh. Okay, I'm on the internet router this way. So obviously this router has no idea about network 192.168, right? 20 or 30. So I would need to add that route. Okay, and branch 2 has 3.3. Okay. 192.168.3.0. Okay, so I added those two routes to both networks. So now my middle router knows about those networks behind those group members. Okay, let's check again. So ping. Now ping works. Yeah, now I have 10 encrypted. Before I had 5, decrypted 5. And if I do repeat 100, yeah, 110, 105 on a group member, 105, 105. That's okay, works now. So now my group members are reachable. I can also do some exclusions, because if you would like to change the policy, you can change the policy on a key server. So if I go to my key server and see the access list, right, I can go there and change this access list. Let's permit IP, or let's exclude something. For example, I would like not to use or encrypt I don't know, telnet. So I can do deny one, because I want to inject this entry before this permit, this first entry. Deny TCP any equal 23. But also I need to do that bidirectionally, so I need to do any equal 23 to any, like this. See? Notice that when I left the configuration, there is a message that the get policy has changed, and I should use crypto GDOI KS, the key server rekey command, to start the rekeying process. In this version, because in the previous versions, after you get rid of the configuration, or just close the configuration of the crypto ACL, the rekey started automatically. Now there is a message that you can run this rekey process manually. So I hit enter, and notice that both got a new rekey message. Okay. Oh, that's funny. It's failed to install policies. We'll see in a second. Okay, let's take a look. The policy is still the same, because that's what we are permitting in the crypto ACL. We have a new SPI. Notice that the new SPI is there. right? It still should be working. So when I ping, it's working fine. But if I telnet, so let me telnet to 192.168.3.3, sourcing from loopback 192. No, okay. Don't remember the password. I think it's admin123. Admin123. Yeah, okay. Right. I just telnetted to branch 2, right? Let's exit out from here. Check this, and I still have 100 encrypted decrypted packets. So my telnet wasn't really do anything. My telnet did not be not included in the policy because I'm denying the telnet. Okay. If I SSH, let's try that. So SSH 192.168.2.2. Can I specify the source? Not really. Encryption. I think it's possible. IP SSH. Source interface. SSH 192.168.2.2. I got rid of that. But anyways, I sent some traffic. Okay, so this SSH should work. Yes, 3.3 exactly. Sorry, Raminder, you're right. I'm SSHing to myself. Exactly. So I was wondering why I see that at branch 1. Obviously. That's a live class. Okay. Exit out and see packets. Yeah, and now I see the packets increased. So SSH works, right? It's being encrypted, but telnet not. But sometimes we have a need to exclude something from encryption just for testing. For example, we know that something doesn't work for some user, and we want to exclude that just, between two group members, for example, in order to test if that's not the issue with additional encryption. So we can do that locally. So locally on a group member, we can exclude, but we cannot include anything, right? Include, we can only through the key servers policy, but exclude, local exclusion is possible. So let's talk about exclusions real quick, right? So let's say we have a group member here that is connecting us to the internet. We have a group member here and another group member here. Right, so for example, if we want to exclude something globally, like my my telnet that I did before, or a good case would be excluding something that is already encrypted. A good case would be the HTTPS that is going out to the internet. I don't need to encrypt that because it's already encrypted, right? So it's a good candidate for a global exclusion, right? On a key server, I go to my IP access list and say deny TCP any equal 443, but remember that you need to add that bidirectionally. So deny TCP any equal 443 to any, because that must work for a traffic to the server and the returning traffic as well. Okay. Local exclusions are working here between group members like this. So for example, I have a host here, that one, and host here, that two, and I would like to exclude their connections temporarily because those users complaining about something doesn't work, and I want to get rid of the encryption just to check if that's not causing the issues, right? So local exclusion is a good thing to do on a group member, right? So again, so we can create an access list, local access list, call it exclude, and deny in that access list. Deny IP host 10.1.1.1 to host 10.2.2.2, and I need to deny also the opposite, 10.2.2.2 to host 10.1.1.1. And then go to the crypto map on my local group members and add match command. Normally there's just set group, right? But I need to add another thing. So let me do that. Example, I will try to exclude that SSH. We'll see if that's possible even. So IP access list extended exclude deny TCP any equal 22 deny TCP any equal 22 any, right? Crypto map get match address, crypto map get 10 I believe, match address exclude. Okay, let me do the same on another branch. Wait a second, show run section crypto map. Yeah, it's exactly the same. Match address exclude. Okay, let's check the crypto. Okay, none. when I ping, oh no, okay, let's do the SSH first. Okay, I'm connected. No packets encrypted. Right, but when I ping, what's that ping? Have it ping 192.168.3.3, source loopback 192.100. Okay, so I locally excluded SSH traffic from being encrypted. Okay, what time is it? Guys, can we take a lunch break now? And after lunch break, I'm gonna start talking about Flex VPN. Actually, Ike V2, that's the thing. I'm not sure if we will finish the whole Flex because it's quite big topic, but at least the theory part will be covered today, and the next week we finish the configuration part of Flex VPN. And then we move, next week is the remote access VPNs, which is also Flex VPN for remote access and AnyConnect as a client for ASA, firepower, and iOS router. Right, so the next week gonna be finish off the last meeting for VPNs. Okay, so let's take a lunch break. "30 minutes as always, so have a nice meal and see you there in 30. Okay, guys, let's continue. So the next topic for today is the Ike V2 and Flex VPN. Okay, so what is the Flex VPN really? It's not the new super hyper a VPN. It's just a different way of configuration to configure something that we already know, which are the overlay VPNs. Okay, so it's we call it a unified way because over the past 20 years, at least, there were a lot of different VPNs introduced, and each of a VPN has a different configuration. So finally, someone actually the original idea came from the Cisco TAC, Technical Assistance Center, to make it more flexible and more maybe easier to configure, even though it doesn't look like it is easier, but it is, believe me. So they came up with an idea to create a new way of configuration for different overlay VPNs, like GRE over IPsec, DMVPN like VPN, or SVTI VPN. So instead of using ton of different configuration, you're just using one simple config, and once you know how to use those, just maybe 10 commands, you will be able to configure everything that you really need. So it's just a unified way of configuring all overlay VPNs. Overlay, that's the key. Okay, like GRE over IPsec, DM VPN, that's the overlay because it's a GRE over IPsec again, or SVTI. And it's based, since it's a new way of configuring, they decided to use IKEv2. So it's based on IKEv2. You cannot actually run FlexVPN with IKEv1. So what's the difference? Let's start with the IKEv2 maybe, because that's the very important aspect of the FlexVPN. So what's the difference between IKEv1 and IKEv2? It's not that big difference. Actually, when you take a look at the IKEv1, remember it was described in RFC 24009 in 1998. Over the past 15 years or so, they added some additional extensions to IKEv1. We already talked about some of them, like NAT traversal, for example, NAT-T, right? NAT traversal. This is the ability to find out that there is a NAT between the routers and or peers, and we can then switch to a different port during negotiation. It was the separate RFC 3947, as I remember. Plus, over the years, they added some additional things like DPD, for example, dead peer detection. We also know it as a IKE keep alives. Keep. Also, in the meantime, they added a config mode. So in the EasyVPN, there was something called EasyVPN, the remote access VPN with IKEv1. So it's not SSL VPN, it's IKEv1 based remote access VPN, EasyVPN. They introduced the config mode. What is the config mode? The config mode is a way to send some attributes down to the client in order to configure the client. So it's a remote access, right? So you have a software client, you build a tunnel between this software client and your headend, like maybe ASA, very popular for that. And during this connection, the ASA will send some attributes, right? Or there are some attributes like banner to be displayed for that user, routing config, proxy configuration, DNS configuration, split tunneling configuration, stuff like that. And there is all of them are optional. There is one attribute that is mandatory, which is the IP address. There must be an IP address in this process delivered to the client, because this IP address will be assigned to the virtual interface that is created on that software client. Okay, and then all the traffic that is leaving this this client will be actually leaving from that IP address. So this IP address is a part of a proxy IDs, remember. So with an introduction of config mode, if you take a look at the phases, so in the phase 1, right, when you're establishing a tunnel, you have a main mode, 6 packets, right? Then you have phase 2 quick mode, 3 packets, right? So notice in the quick mode, in order to establish a tunnel, you need to define proxy IDs. So you need to have some IP address that is assigned to the client, right? And a network that this traffic is going to, like 10.1.1.0. This is the client IP. This is the IP assigned to the client. So when this IP is assigned to the client, it's assigned between phase 1 and phase 2. We call it phase 1.5, which is the config mode or conf mode, right? So the conf mode was introduced to deliver those attributes to the client. And one of those attributes, like IP address, is mandatory. All other attributes like banners, DNS, IP addresses, stuff like that are optional. Okay, why I'm talking about all those things? Because IGV2 is nothing more like the same thing that we have in IGV1 plus all extensions that were added to the IGV1 over the years in the one RFC. It's RFC 5996, by the way. Okay, and it's a IGV2 definition. So it's basically IGV1 plus all extensions. It's like IGV1. Okay, so even if it comes to the negotiation, like main mode, quick mode, delivering all those information in those packets, all the payloads are the same. Right? Plus all extensions. Okay, built in, plus some additional messages. So we don't have a main mode and quick mode anymore. We are delivering the same information, pretty much the same information, in a different order, in a different process. Okay. What else? It's more considered more secure, a little bit, usually simply because it's using cookies to protect against denial of service. So in this matter, it's considered more secure. It's definitely faster than IGV1. And this is because to set up a simply tunnel between two endpoints, in order to do that with IGV1, we need to have 6 plus 3 messages, which is 9 messages must be exchanged to set up a simple, simply point-to-point tunnel. In case of IGV2, 4 messages. Okay, there is a minimum. IGV2 also supports something called NGE. NGE, Next Generation Encryption, or SZ2B. Call it SZ2B. The NGE is the EC cryptography, elliptic curve cryptography. EC, okay, EC crypto. So it's a new way to, or new algorithms using a different, methods to protect data, basically. In case of authentication, in IGV1 we have authentication with pre-shared key, right? RSA signature, and we have in IGV1 RSA encryption as an authentication. So nobody used that. Nobody is using this kind of authentication, so it's not popular at all. That's why they decided to get rid of that authentication in IGV2, but instead they added a new way of authentication, which is EAP, Extensible Authentication Protocol. We're going to be talking about this later, especially in the ICE, in the ICE, Cisco ICE theory. So you'll see how it works. It's mainly used here for remote access authentication, not the site-to-site. So, but pre-shared key and certificate still possible, plus EAP is a new authentication. In case of authentication, there's also hybrid authentication possible. So hybrid authentication is when one site is using one authentication method, another site is using different authentication method. For example, this router may use pre-shared key. This router may use RSA signature. Obviously, it doesn't mean that on the router on the right we don't need to configure pre-shared key. We need, but it's a hybrid authentication. So one way is authenticating using pre-shared key, one way is, or another site is authenticating using certificates. There's also something called an asymmetric authentication. So asymmetric authentication is when you use pre-shared key on both ends, but different keys. So one end is using pre-shared key Cisco 123, another end is using Cisco 345. Okay. Obviously, the same key must be on both ends anyway. Same transport mechanism for IGV2. So basically still UDP 500 or UDP 4500 in case of NAT, when NAT was discovered. So still same thing. And also it supports acknowledgements and notifications. So that was added, supports ACK and notifications. So from the debugging perspective, it's a little bit better. It's more, because of notification, it's telling you what's going on a little bit better, but to some extent, not perfect. Okay, so don't panic. I know that a lot of people are really scared about that. IV2. Okay. So let me show you the packet exchange with IGV2, but comparing to the IGV1. So let's really quick take a look at the IGV1, initiator and responder. Right, in the first packet we have a header, we always have a header, and SA payload, security association, right? We call it actually SA1 because there is another security association payload in the quick mode. So let me put some legend here. SA1 is a security payload, right? The proposal for ISACAMP SA. Okay, the responder is sending its packet back to us with a chosen proposal. Then we are exchanging the key Diffie-Hellman stuff, so header, key exchange, Diffie-Hellman, and nonce, right? Nonce from the initiator, nonce underscore I. Then we have header, key exchange from the responder and nonce from the responder side. Then we have header and the authentication. So we present our ID payload and hash for authentication, hash underscore I. And finally, the ID and hash for authentication from the responder side. 6 packets, that's phase 1 main mode. Then we have 3 packets for quick mode. Right, first is the header again, where the cookies are and so. We have SZ2. So again, now SZ2 is the security association, but this is the IPsec transform set. Basically, right? That's the proposal for data encryption. And the TS, we call it officially, TS is the traffic selector or proxy IDs. So what we going to secure, okay? Respond to that is SZ2 payload with a chosen proposal and a traffic selector from the responder. And finally, we have a header and a hash to finish the negotiation. Right, so in case of that, this is the main mode, phase 1. This is the phase 2 quick mode. Right? What is encrypted? Everything here from this packet onwards encrypted. Right? Now, let's take a look at IGV2. As said, the same payloads sent between the initiator and the responder in IGV2. The only difference is that they may be sent in a different order. So in the first packet, we have a header SA1, which is the proposal. We have a key exchange, so Diffie-Hellman stuff, and nonce I. So notice that everything that is sent in the first packet and third packet in IGV1 is being sent in the IGV2 first packet. the response, the chosen proposal, key exchange for Diffie-Hellman, nonce are. Then we have another packet with ID, our identification. We have a new payload called auth payload, which is basically this hash I and stuff like that for authentication, but this is a new payload because it can support EAP authentication, stuff like that. SZ2, security association from the phase 2 quick mode, like one, and the traffic selector. So again, we are combining two packets together and sending all that data in the one packet. Header ID, auth, SZ2, and the traffic selector from the responder. And we actually done because those two, this is the kind of phase 1, this is kind of phase 2. Obviously, they are not named this way. Actually, this is called IKE_init phase, those two packets. This is the IKE_auth. Okay, and after exchanging those 4 packets, okay, encrypted is here. So those first two packets are clear, the next 2 packets are encrypted onwards. So after exchanging 4 packets instead of exchanging 9 packets, we have a basic side-to-side tunnel negotiated. In addition to that, we can also create a new additional security associations for data traffic, and this is a separate process where we need to send or exchange between peers header, ID, auth, SZ2, traffic selector, because we are basically building a new SA for data encryption. And we also have a new payload here that we can deliver called CP. The CP is the config payload. Remember the easy VPN and the attributes? That's exactly this. So we can exchange some attributes over this config payload. This additional exchange is called create underscore child SA. Underscore SA. Okay, and very important thing is this CP. The CP, the config payload, allows you exchanging some attributes. Right? What can be that attribute? It can be some information about networks, can be some information about the banner, right? All those attributes for remote access. But for site-to-site, it's really nice to have that option because we can exchange information about networks behind our peers. So CP allows to send or exchange, rather. Exchange. Okay, maybe send, because we are not exchanging it. This might be one way only. So CP allows sending attributes, right? Example. Exchanging routing information. about networks behind peers. Okay, this is called IKE V2 routing. So that's pretty cool. What we can do with it, we can, without any overlay additional routing protocol, we can exchange information about networks behind us. Right? But that's pretty cool and very scalable, because it doesn't require any dynamic routing protocol on top of your VPN now. It's just being sent during the VPN setup. There is one disadvantage of that. It's done during the VPN setup. So that means it's not that dynamic. If you add some network behind your router, this network will not automatically show up on the other end. You need to kill the VPN and re-establish the VPN in order to have that network announced. The question in the chat is about okay, what's the flag and how we gonna see it in the routing table. So it's gonna be injected into the routing table as a static. So and we don't, there is no separate flag. I would see that actually, but there is no separate flag for it. It's just static. Sure. Other than CP, are other parameters in the identical to those in IKE AUF? I'm not sure if I understand the question. So can you rephrase that maybe, or give me some more specifics? Okay, I understand. Okay, so you're asking if there are different things, just the CP is added to the create child essay. No, actually the CP, and I believe CP can also be in the IKE AUF. Okay, so it's exactly the same. The difference is just if the purpose of creating some additional SA. If you want that, you need to have a separate additional exchange to create additional SA. That's the only difference. But actually very similar to IKE AUF. And IKE AUF, I believe, can also have CP payload included. Okay, gotcha. Okay, there's one thing that you need to understand here, because it might not be something that came to your mind. Notice that if we are sending the key exchange in the very first packet, the key exchange is what? Is the P prime G generator and the X of A. Okay? And the generator is something that was generated from the group, Diffie-Hellman group, that normally in the IGV1 we negotiated. Here there is no room for negotiation of the Diffie-Hellman group. Okay, so it's a similar problem that we have with phase 1 using the aggressive mode. Aggressive mode was actually very similar to what we have in IGV2. We sent the key exchange in the very first packet, and the requirement for that to work was to hard code the Diffie-Hellman group. The Diffie-Hellman group in aggressive mode was always group 2. Now, so how does it work in IGV2? Is it bad, or what's happening? So actually it is possible to negotiate the group of Diffie-Hellman, but it will not be in the first packet. Let me show you that the process, because now people that were thinking about this and invented that IGV2, their process, thinking process was this. They thought, if we are looking at the typical VPN, when we try to, and two administrators want to set up a VPN between their routers, they agree on the policy. It's highly unlikely that they agree on something different, right? So it's unlikely that they choose a different Diffie-Hellman group. That might be obviously the mistake in a configuration mistake, but normally if the process works, that's gonna be the part of the agreement between those two administrators. So in 99% of cases, that's gonna be fine. Okay, so do we really need to exchange some additional packets in order just to make sure that that was automatically negotiated? Maybe we should just put something ahead and trust our administrators for the correct configuration. So that was the thinking of those guys. So in this case, it is still possible for a Diffie-Hellman group to be negotiated, but the negotiation, it's a little bit strange. Negotiation in IGV2, because it's not really a negotiation. Let me show you that. We have two routers, and let's say this guy have a Diffie-Hellman group 5 configured. This guy have a Diffie-Hellman group 2 configured. So in the very first packet, the SA payload gonna have AES, SHA-1, for example, and group 5 Diffie-Hellman. And the key E payload in the very first packet will have a P, G, and X of A. Right? Remember, the G comes from this group, and X of A comes from the computation where G is used. Right? And all those payloads are included in the very first packet. So what will happen on the responder? Responder will simply drop that packet and send not acknowledge message. Okay. So if it's not an acknowledge message, that means for the initiator, we need to try again with a different settings. So now AES, SHA-1, and group 2. And the key exchange gonna have PG X of A. That again, G comes from a group 2 now, and X of A comes from P and G. And that's going to be sent here, going to be accepted. Okay, so it's not a negotiation as such, it's just a way of not acknowledging something, and then the initiator must try again with a new set of settings. Okay, it's gonna be easier to understand when you see how we configure that in IGV2. Because with IGV1, remember, we had that crypto ISACAMP policy 10, policy 20, 30, and so on, the sequences of policies. In IGV2, we don't have that. We have if it comes to the group configuration, we have a crypto IGV2 proposal, and there is a group 5 space 2 space 14 space whatever the group is. So we are defining one proposal, and the group in that proposal is defined after a space, basically. So we have a list of groups that we can choose from. So I will be talking about this in just in a second now. So to better understand, or let you understand how we building this in comparison to IGV1, let me give you an overview of IGV config blocks. And that should be a good summary for everything. So IGV1 versus IGV2 configuration blocks. First off, in IGV1, we have something called ISACAMP policy. That's the one of the puzzles that we need to have in the config, right? The configuration of that, crypto ISACAMP policy 10, right? And underneath we configure encryption, AES, hash, SHA-1, group, 5, authentication, pre-shared. Right, that's our policy. And then we configure an additional policy with a next sequence number and propose something different. In IGV2, we don't have that. Instead, we have something called IGV2 proposal. Okay, so IGV2 proposal is basically the counterpart of the same thing that we had in IGV1. Okay, how we define that proposal? Actually, we don't need that because in IGV2 we have smart defaults. What are the smart defaults? Smart defaults are default configurations that we can use out of the box. So in this case, we're going to have a crypto IGV2 proposal of a name default. We don't see it in the config. If I do show run crypto IGV2, it will not show it. But if I do show crypto IGV2 proposal, that's going to show me the default settings. And underneath is encryption. And instead of configuring like this with the sequence numbers, we have encryption AES space 3 des space des, okay? Then instead of hash, we have a different command, integrity, okay? SHA-1 space MD5. Then group for Diffie-Hellman. We have a group 5 space 2 space 14 space 20 and whatever the group is. So let me show you that on the router. Show crypto IGV2 proposal. See the proposal default encryption is AES 256, AES 122, AES 128. Basically, this proposal may change depending on the iOS version that you have. The newer iOS version and you have the better proposal might be. Okay, integrity SHA. PRF is the pseudo-random function for for those hashes, right, in the whole process, and the Diffie-Hellman. Group 5, then group 2 defined. That's the default. Okay, but I said there is no IGV2 policy in IGV2. Instead, there is IGV2 proposal, which this is a good name because this is the proposal, right? But I must say that there is IGV2 policy as well. And that might be confusing because this IGV2 policy is not the ISACAMP policy that we know from IGV1. Actually, IGV2 policy is something that is matching the proposal that we have with some additional things. Why we have that for? Remember notice that in IGV1 there is one thing that you cannot do. For example, if you have, let's say you have two peers like that, and you would like to negotiate with this peer ISACAMP policy 1. With this guy, you would like to have ISACAMP policy 2, which means that here you would like to just propose AES, and SHA and group 5. Here you would like to propose 3 DES because maybe that's the old router. 3 DES, MD5 and group 2. Right? With IGV1, this is not possible because this config is global. It works for everybody. So this config will be taken and sent as a proposal to both routers, to both peers. In IGV2, they fixed that. In IGV2, you can change that. You can actually specify what proposal should be delivered to what peer. Okay, and you can do that with a use of IGV2 policy. There is a crypto IGV2 policy of a name default as well, because that's a part of the smart defaults. There is a proposal default already assigned, and you can assign that with a VRF or match it with a VRF or local address, which means that if you are peering with this guy here with a some indoor front door VRF, VRF here, then you can specify, okay, that's gonna be through this VRF. Or if you are talking with this peer over this interface, you can specify, okay, this interface should have only this policy, or should use this policy, this proposal. Okay, so it's much more flexible. Okay, next thing, next configuration block is the key. If we use the pre-shared key authentication, in IGV1 we have ISACAMP key. Right? Or we have ISACAMP keyring. Remember the VRF aware IPsec config? ISACAMP keyring. So two ways of configuring the key in IGV1. In IGV2, we have only one way of doing this, which is IGV2 keyring. Okay, so both are basically related to the same thing. How we configure that? On IGV1, it's a crypto ISACAMP key, right? Cisco 123 address and the address. Or keyring crypto ISACAMP keyring, and so on. In case of IGV2, the command is crypto IGV2 keyring. I'm writing this because the command structure is a little bit strange, I would say, weird. First off, we need to specify a peer name like router1, and this is just a label. It doesn't mean anything, okay? And under this peer, we say, okay, pre-shared, right? Key is this, Cisco 123, address is this. Okay, then we say peer router 2, and again. So it's a one keyring, labels for different peers, and then the keys for those peers. Okay, and obviously the keyring is not a smart default because we don't have a default keyring. So let me put test here, not a default name. Okay. Okay, and finally, the most important piece of configuration in IGV2 is IGV2 profile. So I was also talking about IGV1 profile called ISACAMP profile. That's the optional profile when you want to use the for IPsec VRF aware IPsec in IGV1. Right, so those two actually are related to VRF aware IPsec IGV1. Okay. Config is crypto ISACAMP profile. Okay, same here, crypto IGV2 profile. And also there is no default, but You could possibly use a default name for it, and that makes the life easier because the default profile is already assigned to something by default. We'll be talking about this later. The most important, there are three things that are very important under the profile. Remember, the profile is like a connection catcher. It's catching the connection and handling this connection from our peer. So there must be at least one match command. Okay, you can match based on IP address, identity in the ID payload, or certificate. If the peer is using certificate, you can match using some field from a certificate. You can match with some additional identities like FQDN, stuff like that. Okay, so match is a requirement here. Second is authentication. And third is the keyring. Okay, keyring or PKI, depending on the authentication that you've chosen here. So notice, maybe not all of you noticed that, but here in this proposal, we are proposing encryption, integrity, and group, but we are not proposing authentication, right? So here, there is no authentication. So how is it possible if we are not proposing the authentication? Authentication is not being negotiated in IGV2. Authentication is something that both ends are agreeing on and fixing configuration that must be fixed on both ends. That's why in the crypto IGV2 profile, I need to define the authentication here, not in the proposal. Okay, so that's the negotiation part. The whole IPsec config remains the same. I mean, IPsec config is like a transform set, IPsec profile, all remains the same. Right, so only the negotiation part, the ISA comp part is changed. So in a real life, you just need to focus on those things like profile and optionally the keyring if you're not using certificates for authentication, but using pre-shared keys. So actually, more like 80% it's already configured for you. You don't need to touch it. If you do it wise, I mean, if you are understanding that there are some smart defaults and you could possibly use them, then your life is much easier. Let me show you that. The Flex VPN smart defaults. How they are related to each other. That's important to understand how we can use them. So you know already that IGV2, some of the IGV2 configuration blocks are pre-configured. Right? Pre-configured, and you know the name of that with name default. right? So first off, we have a crypto IKv2 proposal of a name default, right? There is some config underneath. Then we have a crypto IKv2 policy of a name default. And that policy has a proposal default associated with it, right? So we have this associated here. Okay, so I would say 80% is already configured. Okay, and you can adjust what's left. You can even adjust or change the default settings if you want. Okay, so you can, if you type in the proposal default, hit enter, there's gonna be some warning that you are changing the default settings, but you can do that. You can override the default settings if you want to. You can remove that. You can do no crypto IKv2 proposal default to get rid of that from the config. Okay, so what is left is actually IKv2 profile to be configured. This is what you need to do. Okay, so you can use crypto IKv2 profile. You can give it a name like your own name, or you can use the default as well if you want to. I will show you that in a second, how we can leverage this default profile name. Under the profile asset, there must be a match command, match identity. So you're usually matching based on the address or certificate. And then you need to specify something called a certificate map, just to match for some specific field inside the certificate. Then second, authentication. Right? You need to define two authentications, local and authentication remote, because it might be hybrid authentication, right? So locally, I want to use pre-shared keys. And remote is authenticating to me with RSA signature. That's the hybrid authentication. Once I have this authentication defined, I need to take a look, okay, what is the remote authentication? So remote, my peer is authenticating itself with a certificate. So I need to specify a keyring. Now I need to specify the PKI trust point because I'm going to be validating his certificate. Okay, so the third thing is the keyring, right, for pre-shared key. Actually, if I'm using locally pre-shared key authentication, I need to have a keyring as well. Keyring and PKI trust point defined, both. Right? So this is our connection catcher. We are catching the connection and handling the connection this way. Okay, and then when you have a crypto IPsec config, we also have smart defaults for crypto IPsec. The transform, the set is a default as well. ESP AES and ESP SHA. And also we have a crypto IPsec profile of a name default. And under this profile, we have a set transform set. Default. And guess what? We have a match IKE v2 profile default as well. That's why it's now this transform set is here, but if you use your profile and you give it a name default, you have it already assigned here to the IPsec profile. So actually, if it comes to the tunnel configuration, interface tunnel 0, if you have a tunnel protection, IPsec profile default, right? So this profile default is going to be assigned here. Right? So notice everything is pre-configured. The only thing that is left is this connection catcher. The only thing that you need to really configure is this connection catcher. I'm gonna configure that in a second. In the lab, so you'll see. Okay, so what we can configure with a Flex VPN? Basically, why Flex VPN? There are 4 different use cases for that. Simple site-to-site VPN. So we have basically this kind of configuration that can be SVTI config or GRE over IPsec type of configuration, site-to-site. It can be a hub-spoke topology. Right, so that's the situation when you have a hub and you would like to just have a connectivity to the hub. Again, this is GRE over IPsec, most likely, or part of a Flex mesh config. Then spoke to spoke. So this is kind of DMVPN-like configuration, right? So you can set up hub and spoke, and also spoke to spoke tunnels, GRE over IPsec again, or Flex mesh. So this is basically Flex mesh config, which is like kind of DMVPN phase 4, you can call it. Judy is asking, is there any link between the IKE v2 profile and the IKE v2 policy? Um, I don't think so. I don't think so. I would need to check, but I don't think so. We'll check that in a second on the router. And finally, remote access. This is something that we're gonna talk next week. So this is pretty cool because as a remote access, you can have as a client another router. We call it hardware client, or it can be a host with any connect, but again using IGV2, not SSL. Okay. As a remote access, you may use also a Windows native IGV2 client. So from Windows 7, I believe, there is a IGV2 native client built in. Or you can even use a third-party remote access clients like Strong Swan. That's a Linux IGV2 based remote access client, right? So it's very, very flexible. It can, everything that is basically based on IGV2 can be supported by the Flex VPN headend. Okay, let me go to the lab and configure basic site-to-site VPN with Flex VPN. So I'm gonna do that on branches. I will get rid of my get config first. Question in the chat, IGV2 or SSL better for remote access VPN? From the security perspective, there is no difference because it's just a different way of setting up a VPN tunnel, and then everything else is done the same way. So encryption is exactly the same. It's AES 256 or whatever. This is just a different way of setting up the tunnel. For me personally, SSL is better because it's more flexible. It can work through the proxy. IGV2 will not go through the proxy. So if you are not on the internet, directly on the internet, you may have a problem with setting up remote access VPN. So SSL is more flexible in that way. It's also using UDP, so DTLS, right, as a transport, which is faster than, I would say, than ESP. So in my opinion, SSL is better for remote access. Sure, no problem. Okay, so go to interface geek 2 and check that crypto map. Get rid of that crypto map as well. Okay. You see the crypto config. Okay, so I have a group. So let me get rid of that as well. Get rid of that as well. Just clearing the whole crypto config. Okay. So now I can configure site-to-site VPN, GRE over IPsec with tunnels, but with Flex config, Flex VPN config. So first off, the proposal is there, right? Do show crypto IGV2 proposal. The policy is there because policy is by default matching the proposal of a name default. Okay. I'm gonna be using RSA signature authentication, so no pre-shared key, so I don't need to configure keyring. I will just configure the crypto IGV2 profile of a name default. Notice that IGV2 default profile attached to the IPsec default profile. That's cool. And there are two things that must be configured under this profile: local and remote authentication and match identity or match certificate. I'm gonna be using, actually I can use match identity depending on what's inside my peer's identification. I can specify what will be in the peer identity. So I'm gonna be matching identity based remote based on FQDN. Let's say that's gonna be branch 2 lab local. I'm gonna match this. On branch 2, crypto IGV2 profile default gonna have identity local of FQDN branch 2 lab local. See, so branch 2 will be identifying itself with this FQDN. This information gonna be in the ID payload of the IGV2 negotiation, and branch 1 will be matching for that. Okay, so I'm gonna do identity as well here, identity local FQDN branch 1 lab local, and I'm gonna match identity remote FQDN branch 1 lab local here. Oh, here we go. So matching is done, identifying itself and matching on the other end. Now I need to say what will be the authentication. Authentication, I need to specify local and remote. Local will be RSA signature, and remote will be the same. Right? Same on the other end. Local and remote. And since I'm using RSA signature authentication, my peer will send me its certificate, so I need to be able to validate that certificate So I need to specify the PKI trust point name to validate that certificate. I'm not sure what is the name of that, so do show run section crypto PKI. CA is the name of the trust point. Okay. Okay, probably the same name on the other hand. Okay, that's done with my profile. Now I know that this profile is automatically. I don't have it. Let me get back real quick to. Okay, this one. So remember, when I use the profile IGV2 profile of a name default, that is automatically assigned to the IPsec profile of a name default. So it's just for me to go to the interface tunnel and apply tunnel protection with a name default, and that's going to be automatically assigned. So I'm going to do a tunnel config IP address 172.16.1.1. It's called. Maybe let's use 1.1. So I'm just configuring basic tunnel source gig2 point-to-point tunnel destination is this IP address, and the tunnel protection IPsec profile default. Right, same here, interface tunnel 0, IP address 172.16.1.2, tunnel source gig2 tunnel destination is this, tunnel protection IPsec profile default. Okay, here we have tunnel app. Okay, I see the IGV2 SA. Okay, I see the IPsec tunnel. Right, if I do show IP route, I don't see this obviously because there is no routing over this tunnel. Yeah, I would need to add this. This is one. It should be 1, 2. Okay. Okay, ERGRP established. Show IP route ERGRP. Okay, now I see that network 2.0 is over the tunnel 0. 3.0, okay. Now I should have some encrypted decrypted packets because of ERGRP hellos. I can ping 192.168.3.3 sourcing from loopback 192. 100 packets went through. How do I know that this is IKV2, not IKV1? If I do show session active, I see IKV2 SA, right, between those two peers. And if I do show crypto map, it should be there. Not information about IKV2 now. Yeah, so show crypto session active. That's the best way to tell that. Right, so show run section crypto IKV2. That's the whole configuration I have on a router right now. In case of IKV2, just the profile. I use the name default because I know that default is the profile that is already assigned to everything else. I'm just matching the identity that my peer is providing. I'm locally identifying to the peer with this FQDN, authenticating both peers with certificates, and the PKI trust point to verify the certificate from a peer is assigned. That's it. Simple site-to-site VTI configuration. It's not SVTI really, because SVTI is not using GRE. This is the GRE over IPsec with tunnel protection, basically, what I configured with IKV2. Yeah. So next week, we'll start with configuration of, actually, I will talk about Flex Mesh. And we will be configuring Flex Mesh config. So it's a DMVPN-like config with Flex VPN. We do the IKV2 routing. I will show you how to do that. And then we move to the remote access VPNs. So we start with ASA config for remote access, and then we move to Firepower and iOS with remote access as well. Okay, Raminder is asking, how do we do failover over site-to-site VPN with multiple ISP links, but not using dynamic routing? That's difficult. With multiple ISP links, that's difficult in case of typical configuration. But with Flex, that's much easier to be achieved. I will show you next week how we can do that with a Flex VPN, because Flex can give you some additional features that you can use in case of dual ISPs. Because the tunnel source, normally you need to specify the tunnel source, right? If you have two ISPs, meaning you have two interfaces, you need to have two tunnels. But with FlexVPN, you can still have one tunnel, but the source of that tunnel can be dynamic. Right? It can be one ISP or other ISP. So that's the really nice thing about FlexVPN. Yeah. Okay, guys, I don't want to go any deeper today with that because the next topic will take us like at least 1 hour to cover. So I don't want to kill you by the Flex VPN Flex Mesh config. I hope it was informative for you today, what we covered today. Thank you very much for being with me, and yeah, see you next week. Have a great rest of the weekend. Cheers. Bye, guys.